Yeah.
Let me welcome everyone. A very good morning from India, and for you, a very good afternoon, Stephen, from India.
Oh
It is
no,
a
it's
pleasure.
11 o'clock at night for me.
Oh, okay, okay. So it's right, and it is very pleasure to welcome you all on this third day of our webinar series. Today we have the privilege to host Stephen Wolfram, who will deliver a talk on reversibility and irreversibility in cellular automata and physics, with an interlude on the life of Ed Fredkin. He has authored an insightful piece titled Remembering the Improbable Life of Ed Fredkin, highlighting Fredkin's contributions to the field of computing and his unique life story. Before we proceed, I would just like to briefly introduce our esteemed speaker. Stephen Wolfram is the visionary creator behind Mathematica, Wolfram Alpha, and Wolfram Language. He is also the author of A New Kind of Science, the founder of the Wolfram Physics Project, and the CEO of Wolfram Research. Wolfram's educational background is as distinguished as his professional career. He studied at Eton, Oxford, and Caltech, earning his PhD in theoretical physics from Caltech by the age of 20. His first scientific paper was published when it was just 15. So, throughout his career, Steve Wolfram has been at the forefront of scientific computing, beginning his work with computers in 1973. In 1979, he initiated the development of SMP, the first modern computer algebra system, which was released in 1981. At the same year, Wolfram was honored as the youngest recipient of a MacArthur Fellowship in recognition of his innovative work in physics and computing. In late 1981, he embarked on a groundbreaking new scientific path aimed at exploring the origins of complexity in nature. His pioneering use of cellular automata for computer experiments starting in 1982 led to numerous significant discoveries about complexity, establishing the foundation for the field now known as complex system research. We are thrilled to have Wolfram here today to share his insights on reversibility and irreversibility in cellular automata and physics, with an interlude on the life of Ed Fredkin. Thank you so much sir, and it is our pleasure to hear from you. Over to you, sir.
Thank you. By the way, you're very welcome to record this. I don't know if you set it to record, but you're very welcome to record this. Is it recording? If
Yes,
you're not recording it, I can record it. So
it has been recorded, sir.
okay. The all right. So I actually want to talk about three things today, which is going to be challenging. I want to talk about understanding reversibility and irreversibility in cellular automata. I'd kind of like to tell you about something new that I discovered about very simple cellular automata just in the last couple of weeks that tells us a lot about biological evolution. It was a big surprise to me because I've been studying cellular automata since the beginning of the 1980s, and I thought I knew a lot of stuff about the simplest cellular automata, and this was something new. So I want to tell you a little bit about that. I also want to tell you about Ed Fredkin, who I knew for about 40 years, and who was a very wonderful and colorful character. And I wrote a kind of obituary piece about him, which turned out to be the most complicated obituary piece I've ever written. He had the most complicated, most hard to decode life, and had told the most stories to me, which I remembered and had a chance to explore. But let me start off by talking a bit about reversibility and irreversibility. And I want to tell you about, let's see, let me just go ahead and share this. So I want to tell you a bit about kind of the story of reversibility and irreversibility. Maybe I can, gosh, this doesn't look quite as easily as Zoom, does it? Oh, no, it finally did that. Okay. Maybe I should, yeah, okay. Let me start off with a story from my distant past. I kind of got interested in physics when I was 11 or 12 years old. And one of the things that was a kind of very early inspiration was an interest in the second law of thermodynamics. And actually, I think I even pulled it down from my library here. I have a copy of a book that has a cover illustration, which is about kind of the second law of thermodynamics. It shows a bunch of gas molecules starting off in one corner of a box and then progressively randomizing through the course of time. If I open this book, you might be able to see it. I don't know if you can see it where you are. Let's see. Oh, there we go. Yes, you might be able to see there that it's a younger version of my better handwriting that says Stephen Wolfram, June 1972. So I bought this book in June of 1972 when I was 12 years old, and I was very interested in this kind of process of randomization that was on the cover of that book, and I kind of maintained that interest for 50 years, and finally, just last year, I published a book about the second law, and you might notice the similarity of the cover of this book and the cover of the previous book. And I finally figured out kind of how the second law works. It took me about 50 years. I don't feel quite as bad about it because I made a quite detailed study of the history of the second law, which kind of originated in the 1820s and then more clarity in the 1860s. And people have been trying to understand why the second law is true ever since the 1860s. So I didn't feel quite so bad that it took me, I think, 50 years to figure it out. But I want to tell you a little bit about sort of the second law and why the second law is true and how it relates to reversibility and reversible cellular automata. And then maybe I'll segue to talking about Ed Fredkin and how this intersected with his kind of life and times. And then I'll tell you a little bit, perhaps, if we have time, about the things I discovered about cellular automata and biological evolution very recently. I just posted something about it a week ago today. All right, let's go back to looking at some of the story. Let me see if I can share this again. Okay, to the story of reversibility. Okay, so this is a kind of a typical version of something like what was on the cover of the book. You start off with a collection of particles in a very orderly fashion, and then over the course of time, they get more randomized and more disordered. What's going on there? Well, we can make kind of a 3D version of that picture. We can kind of see the structure of what's happening, and that kind of shows us the dynamics. And we can kind of we can project that and so on. But now let's see what's the essence of what's happening here. What we had looked at originally here were a bunch of essentially billiard balls bouncing according to laws of mechanics. But we can simplify that quite a bit. So for example, we could have square billiard balls so that we don't have all of the kind of hitting off center and scattering further away dynamics of actual billiard balls. And you can see the same kind of 3D pictures in space and time for these kind of square billiard balls. Well, we can simplify even further, and we can just have something like this array, discrete array of kind of.
Sorry to interrupt. We can just see the grid view, not the. Individual.
Okay, well, maybe we shared the wrong. Oh yeah, that's terrible. Okay, present something else. That's no fun at all. Okay, let's see. That's really weird. Entire screen. Okay, how about that?
Yes.
Better?
Thank you very much.
Okay, all right. So let me repeat then. If you didn't see any of this stuff, I need to show you. So this is a bunch of billiard balls bouncing around. And this is the 3D view of that. This is what happens if you make them square billiard balls. and that's kind of the dynamics of those. And this is now the next level of idealization of just arrows on a grid. And if we keep going here, we can make that, we can kind of idealize that further, and pretty soon we realize we have a 2D block cellular automaton. And in fact, you can see the dynamics of that by realizing that you can just consider kind of 2x2 blocks, and you can update those 2x2 blocks using rules like this. In fact, you can simplify even further to just say the rules that we're using are these rules. And the fact that these rules go sort of in two directions is the way of recognizing that there's reversibility, that every block has a block that it is transformed into, and the block it's transformed into can transform back. So what happens with this rule? You can start off, if you have an array like this, you'll find that the thing sort of recurs quite quickly. You can kind of see that happening in these 3D pictures. But as soon as you introduce even the slightest imperfection here, you'll find that you have something very much like second law behavior. You'll have something which starts very orderly and eventually becomes quite disorderly. And you can kind of see that happening in this 3D picture here. And it's the same story. You can look at this in a variety of different ways. It's the same story of a two-dimensional cellular automaton. And so what you're seeing is there is reversible dynamics, but the sense you're getting is that even though the dynamics is reversible, after if you run that dynamics like forward in time, you will quickly get something that looks random. Well, now you can simplify even further, and you can look, for example, just at a one-dimensional cellular automaton, and in a two-color one-dimensional cellular automaton, you'll have very simple behavior like this, where particles just essentially cross over each other. But as soon as you have three colors, you can get very different kinds of things going on. So that's an example of what happens with that three-color rule. And here's kind of the most notable thing. Here you're starting it off from a sort of regular array of cells at the beginning, and what you're seeing in these successive panels is increasing apparent randomization of the behavior. And you can look at this for a variety of different rules. Here's another rule. You can see what's happening here, again, is that you start off from something that's very simple, and pretty quickly you're getting something that looks really complicated. And you can start measuring. So when you're trying to understand the phenomenon of irreversibility, it's a typical phenomenon in what we observe in the natural world, that you will see things where something goes from being very orderly to being, for example, you take I don't know, an egg or something and you shatter it. It starts off very orderly, looking like an egg, and it ends up as a big mess. And what we see happening is things shattering like that, but we don't see the reverse operation of the egg with all its pieces reassembling itself into that original orderly egg. So it's kind of a mystery how the dynamics of the underlying system can be reversible, in the sense that every individual molecular collision is reversible, yet the overall dynamics of the system seems irreversible. But we can get, from these systems, we get a clear sense of what's happening. So here's an example where in the middle here, we have a very orderly arrangement. It's just a bunch of identical cells in a blank background. But as we go forwards in time, the thing progressively randomizes. And the same is true when we go backwards in time. And so what we realize is that the important fact is that as we go forwards in time, there's sort of a computational process that's encrypting kind of the simplicity of the initial conditions here. So we only get to see something that looks complicated to us. The same will be true if we went backwards in time. But what we're seeing there is that what's happening is we have carefully prepared this simple state of the system, and whether we go backwards or forwards in time, it will get to have sort of more computation spent on it, and it will be something that for our purposes kind of looks as if it's encrypted the simplicity of the initial conditions. And there's kind of a long story about sort of how the second law works by understanding kind of the computational process that represents this kind of encryption of the initial data. But in the end, this is a reversible one-dimensional cellular automaton that's doing all of this. And you can start seeing, you know, if we measure various properties of the system, you can measure that on average, things seem to be random, except in that middle place where we had carefully prepared that state. And so sort of the bigger picture we can look at from a pure sort of cellular automaton study point of view. We can look at all kinds of things. If it's a finite size system, it will be periodic. We can look at its cycle structure. We can do all sorts of analysis of that. We can find there's a more complicated cycle structure and so on. We can see that all these various properties of cellular automata kind of show up as being significant in the phenomenon of the second law. Now, you know, we can also study things like the concept of entropy. We can study how this sort of works in traditional thermodynamics, and how sort of the cellular automaton, you could start off with a higher density of particles. You can think of these as in the central region here, and it will gradually diffuse out and so on, just as we expect in standard thermodynamics. But essentially, the bottom line here is that what we observe in these simple cellular automata is a really clarifying model of the phenomenon of thermodynamics, of the phenomenon of the second law. When people talk about the second law, they often talk about kind of the energy of particles and all sorts of other things like that, but none of that is important. What's important is the pure computational process that can be captured by something like this one-dimensional cellular automaton. So we can study a lot kind of different cases where sort of second law behavior occurs, where things get sort of progressively more random over time. These are reversible cellular automata where that's happening. And we can see there are all kinds of things that happen. Sometimes you'll get these very nested patterns. Sometimes you'll get other kinds of things going on. One of the things that is particularly interesting is you get these cellular automaton rules that are just reversible cellular automata, where it just looks like somebody kind of planned it that way. Somebody was trying to, for example, here's an example of one of those cellular automaton rules that looks like it is performing kind of an organized operation, even though in the end, it's just a cellular automaton rule. And I think this phenomenon where these reversible cellular automaton rules can do these things that look as if they correspond to mechanisms that we designed, I think this is importantly related to phenomena in biology, where, and I kind of describe it as kind of the mechanoidal phase. It's kind of, it's not a solid that is very regular like a crystal. It's not a liquid where everything is quite random. It's a kind of a phase in which it seems like everything is orchestrated to have all kinds of mechanisms. And I think there's a really interesting set of things to investigate in these kind of mechanoidal cellular automata that are just examples, for example, here of one-dimensional reversible cellular automata, to try and characterize this kind of bulk orchestration, this bulk organization of these systems. You know, I think I maybe, having talked a little bit about biology here, maybe I should segue and talk a little bit about the thing I just did last week, and then we'll talk about Ed Fredkin. So the question that I was asking is, why does biological evolution work? It's a very similar question to the question of why machine learning works. How can you kind of go from, how can you actually satisfy the complicated constraints of the fitness of an organism from something which has just kind of a genotype, just a genome that specifies certain rules? So here, this is just a pure cellular automaton play. This is just an ordinary cellular automaton with 3 colors, 27 cases in its rule, and it starts off from just one red cell here. And in this particular case, this particular rule, it lives for 51 steps and then it dies out. So now let's imagine this is kind of the genotype of a biological organism. this is its genome, this is its phenotype, this is sort of the behavior it produces. So now let's say we're going to mutate the genome, as happens in biological evolution. We're going to apply a series of point mutations, 1-bit mutations to that genome. Well, now we can ask, let's say we apply those 1-bit mutations and we only accept a mutation when it makes the organism no less fit than it was before. And by fitness here, we're going to mean the organism lives as long as possible, but without dying out, but not an infinite time. So what happens then is this is a succession of different cellular automaton rules that were obtained from each other by 1-bit mutations. And so what we see is the thing sort of learns over time how to survive for 50 steps. Here's a different way, a different path for learning, a different thing it learnt. Here's another one. And what's really pretty interesting about this, I think, is it's like these are different organisms at different moments in the fossil record. And maybe you see, you know, in the Permian period, you might see a little organism that looks like that. By the Cretaceous period, it's kind of embellished itself to be more successful at what it's doing and to live longer. So this is kind of a way in which kind of sort of the complexity of is kind of brought into the system by the adaptive evolution trying to make the system kind of live as long as possible. So just to fill this in a little bit, if we start from a given case, a given rule, and we just look at all 52 possible mutations from that rule, you'll see all sorts of different behavior. And many of these are like it lives forever. We don't count that. Some of them it dies out more quickly than it did here. But there's just one example here where it lives longer than it did before. And so that would be a case where we would say, okay, at increased fitness, we'll keep that mutation. And so we'll see a series of mutations, and eventually the mutations will build up to the point where the thing lives longer. And so if we look here, there are often many steps between the longer lived waypoints, so to speak. And we can look at that. Here's just a plot of how long did it live against the number of mutation steps that we used. And so there's a long period, a long plateau where it's making mutations, but they're not letting it live any longer. And then eventually it breaks out. Well, it did that earlier here, but eventually it breaks out and manages to live a lot longer. And we see that precise phenomenon as we look at those. As we look here, there's that long plateau, a 3,000 step plateau, and then it breaks out and eventually it discovers how to live for 51 steps. So what's interesting about this, you can study these things in all sorts of different ways, and you can look at all sorts of different rules and see how they progressively adapt to satisfy this fitness. You can also look, here are elementary cellular automaton rules, and that's a rule where everything is blank, so it just dies out after one step. You make some 1-bit mutations, and this thing will live maybe one extra step. Now, you can make a multi-way graph of the kind that we've done in our physics project, where you say every arrow here is a mutation. So here it's just the blank rule, and it dies after one step. Here we've got to rules which live 2 steps, and so we keep going, and we're getting to rules which live more steps. And so this is kind of a complete trace of sort of the history of biological evolution for this system. And you can keep going. This is the case of a r equals 3/2 2-color rule. These are evolution paths there, where you see the thing eventually living quite a long time. You can make kind of the multi-way graph that shows the complete history of all the kind of speciation of this organism. And you can actually go ahead and do that for symmetric. Let's see, where is it? That's symmetric 2-color second nearest neighbor rules. And what you see here is is sort of speciation. You're seeing on this side, it has one kind of idea about how to live a long time. And on this side, it has a different idea. And you're sort of breaking these 2 branches in the tree of life here. And if you're into things like fitness, landscapes, well, you can look at kind of how you see in the space of possible rules. This is now, you know, we're progressing, we're adaptively evolving in rule space. And for each rule we reach, we're figuring out how does the organism grow. And this is kind of showing how the kind of local view around different places in rule space, and how we kind of go to how we go to a rule, a different possible rule in rule space. And we can kind of draw these sort of fitness landscapes of which rule corresponds to what position in the space of possible rules, and so on. We draw some complicated pictures of that. It's perhaps interesting to see, okay, just for fun, we can look at some exhaustive searches. There are a lot of rules, as many of you will know. As you increase K and R, there are lots of rules. If you take all possible rules, there are slightly less rules if you have symmetric rules. And you can ask the question, kind of, what are the longest lived rules in these cases? So let's take a look. These are, it's a little hard to see here. Here, let me show you a different case here. Well, okay. These are symmetric 3-color rules. No, actually, this is showing. Sorry, this is. Oh, where do I have these? I wanted to show you. Yeah, here we go. Oh gosh, this is a bit small. Okay, these are the longest-lived 2-color second nearest neighbor rules, and so you see, there's a rule that lives for 308 steps here. And what's kind of interesting is some of these rules you can kind of guess the mechanism by which they're lasting for 151 steps, for example. But by the time you're at 308 steps, if you saw that as the thing that a biological organism figured out to live for 300 steps or whatever, you would think that was just sort of you would not, you kind of be surprised that it works. It's a discovery from this adaptive evolution. So in any case, we can look at these things, let's see, we can ask questions about kind of well, we can, instead of evolving to live the longest time, we can do things like evolve to live exactly 50 steps, or evolve to live exactly some other number of steps. We could do something like, say, evolve to be as wide as possible, and those are the rules you get there, or evolve to have exactly a 3-to-1 aspect ratio, or evolve to have roughly a pi-to-1 aspect ratio. And all of these are things that you get to by sort of progressively adapting in the space of cellular automaton rules. Anyway, I thought you might be interested to see that. It's a recent thing that I discovered just looking at. You might have thought that everything one could say about elementary cellular automaton rules had already been said, but you would be wrong. All right, let's talk about Ed Fredkin, longtime enthusiast of cellular automata, longtime friend of mine. And I want to tell you kind of the some of the okay, so I want to tell you some of the sort of story of Ed Fredkin as I encountered it. So where is this? What has this done? I am not used to using Chrome for this. Let me see. How is that going to work? Maybe that will work. Okay. So what was the story of Ed Fredkin? Well, that's a picture of Ed. Ed, I first met Ed in 1982, and I knew him quite well. He lived fairly near to me in the Boston area. I saw him quite frequently. I'm not completely sure he ever listened to anything I ever said. And although he used our technology, Wolfram Language and so on, for many years, for 35 years, and he would tell the wildest stories about his life. And I wasn't sure whether these stories were really real or not. Only after he died did I really go back and say, I'm going to find out the stories behind these stories. It turned out they were pretty much all true, and they were really wild. So let me tell you the kind of the life story of Ed Fredkin. He was born in Los Angeles. I actually didn't know that until I was writing this obituary. Maybe he told me once, but I didn't really know that. And his parents were both from Russia. And his father actually had studied engineering right before the Russian Revolution, and his studies have sort of been cut short by the Russian Revolution. He came to LA, and he met Ed's mother, who was a concert pianist in LA. She was also from Russia, and they had a Ed's mother died when Ed was 11 years old, and he had various half siblings and so on, including a brother who is 6 years older than him, who we'll hear more about later. Well, the first kind of notice of Ed in the public record came in 1948, and it's a newspaper article about the first boy to get aboard the Freedom Train. That there is Ed Fredkin in younger form. And actually, that newspaper published an article, I think it's Ed's first publication, by Ed Fredkin. It says, by Edward Fredkin. And what was the story here? This was a time when the US was kind of pushing patriotism, and they had a train that had a bunch of the artifacts from American history, US history, on the train, and it was, you know, riding around the country for people to come and sort of see this museum on wheels of American history. And Ed, in a very typical way for Ed, kind of created a story around himself, because he decided to get up at 2 a.m. as a 13-year-old kid and go be the first person who's going to get on this Freedom Train, as it was called. And this was the story of Ed describing his adventures there. So that was kind of the first Ed's first publication and first kind of public visibility. Well, Ed went to high school after that. His performance there was a bit spotty, although, as he told me, he figured out very early on how to sort of game multiple choice tests, because there was a time when multiple choice testing was just coming in, and he'd figured out sort of a way of improving the odds. And the result was that he scored really a high on a sort of statewide IQ test in California, because he'd figured out kind of how to sort of game the which the possible sort of choice it couldn't be in the multiple choice, and so on. Well, after high school, Ed applied to Caltech, which was actually only 13 miles away from where he lived, and largely on the basis of his test scores, he was admitted to Caltech. And he ended up being, doing various odd jobs to support himself when he was there, didn't do much homework, and before having to pick a major in his sophomore year, he dropped out. Told me a bunch of interesting stories about his time at Caltech. I could repeat some of those, but maybe we should move on with his story. But Ed had always been interested in machinery. And when he was younger, as he tells it, he kind of had a business fixing radios and things for people. But in his first year at Caltech, he decided to learn to fly an airplane. So he did that. Actually, his older brother, Norman Fredkin, had been in the Air Force for a number of years. Well, actually, there's a picture that I found of the older Fredkin, who flew a bunch of missions in the Korean War, surveillance missions in the Korean War, and that was the older Fredkin, complete with his plane. But the younger Fredkin, Ed Fredkin, age 19, this is 1954, drops out of Caltech and joins the Air Force. And so what happens then? Well, he's sent to an airbase in Arizona, and by the summer of 1955, he's qualified as a fighter pilot. And Ed always used to tell me these stories. Ed was an enthusiast of airplanes his whole life. And he would always tell me these stories about his sort of adventures, flying a plane, trying to get it higher than anybody had managed to get it before, flying a plane in parabolic flight and putting an eraser in front of his nose, kind of suspended in midair, and just sort of tipping the plane very carefully to keep the eraser suspended in exactly the right place so the plane was flying in its perfect parabolic trajectory. But in any case, Ed was flying planes, but in 1956 he ended up being grounded because he had asthma, and he wasn't sort of he wasn't sort of perfect enough in terms of health to really be a fighter pilot who was going to get to operate in that way. So he ended up being sent to an airbase in Florida to be what's called an intercept controller. Air traffic controllers have the task of keeping planes apart. Intercept controllers have exactly the opposite task, which is they're trying to tell fighter planes how to intercept a bomber to shoot it down. So he was an intercept controller responsible for talking to fighter pilots to guide them to bomber targets. So, okay, that was all done sort of by hand in the US at that time. But there was a big project called SAGE, the Semi-Automatic Ground Environment Air Defense System. And its goal was to take all the radar information coming from radars all across the US and bring them together in one central place with computers to get kind of a global view of kind of the airspace around the US. And at that time, this was sort of the first decade of the Cold War. And at the time, it was like, maybe the Soviets are going to do a first strike against the US. We have to be able to detect that happening. We have to have kind of central control to see that, to see their bombers coming. Well, Ed was Ed ended up being sent by the Air Force to be part of testing, supposedly testing the SAGE automated, doing the thing that automated his job. It was kind of like AI in modern times. The AI was going to automate the intercept controller's job, but they were sending some intercept controllers to go see whether this automation was actually going to work. So as Ed told it to me, they show up in Massachusetts at Lincoln Lab to kind of test the SAGE system, and they're told by the companies that are building SAGE, IBM and AT&T and so on, that oops, the project has been postponed for a year. So there they are in Massachusetts with nothing to do but wait for a year. Well, at the time, the Air Force was really keen to train people to use computers because very few people knew anything about computers. And so they put on this course for people to learn to use computers. And Ed ended up staying in the Boston area to take this course on how to use computers. And as he tells it, basically, he was the only person who lasted, at least from the Air Force, who sort of lasted in this course. And so the result was that he learned a whole bunch about computers from this course. Now, I have to say that Ed, I think, concluded at the time that he was the world's best programmer. And even when, you know, in his last years of his life, he was still telling me that he was describing himself very matter-of-factly as the world's best programmer. Now, at the time when Ed learned to be a programmer, there were only a few tens of people who knew how to program computers in the whole world. Obviously, by the time Ed died, there were hundreds of millions of people who knew how to program computers in the world. And so maybe Ed's claim that he was the best programmer was a little less convincing. But in any case, so Ed remained at Lincoln Labs, initially in the Air Force, doing essentially computational odd jobs and connecting different computers together and so on. When Sputnik was launched in 1957, he was sort of pulled in to do some emergency programming to figure out things about the orbit of Sputnik. Sputnik was a big surprise. I don't know how much history you guys know, but this Sputnik was sort of the big surprise that the Soviet Union managed to launch an artificial satellite before the US. The US could have done it earlier, but didn't bother. And so that was kind of a real wake-up call for the US to improve its technical capabilities. And Ed was sort of pulled into the early weeks of that. Ed kind of relished hacking the bureaucracy in the Air Force, like being given a stamp that said secret that he could stamp documents with, so that he could read documents that he himself had written, which otherwise he would not be allowed to read. So in any case, he stayed at Lincoln Labs, and at some point he decided to leave, and he wanted to start his own company. He'd been sort of interested in commercial things from the beginning. He wanted to start his own company, and he went to visit a company called Beranek and Newman, BB&N. And he saw there a person called Licklider, JCR Licklider, who was a psychologist, actually, who was an early person involved in the idea of kind of computer-human interfaces. But anyway, Ed went to work at BB&N, and and he wrote his first paper, one of his only actual academic papers there, about what's called trie memory. And the idea, maybe we don't need to go through in detail what this is. Tries are kind of a data structure for storing. It's not a tree, but it's something where you are this is, for example, a trie that stores words in English that contain the letters in the word wolf. So here you'll see the word wolf, and you'll see woof here, and so on. And you're storing only those parts of the tree that you actually need to store to get the particular words that actually occur. It's not all possible elements of the tree, it's just the ones that are needed for the words that occur. And tries are what are used, for example, in spell checkers. Spell checking is all based on tries, and a bunch of data retrieval technology is now based on tries. But Ed invented this thing he called tries, TRIEs, and he actually invented this while he was in the Air Force. Just to give a sense of, at that time, Ed was kind of into making sort of pseudo computer pictures and so on about these things. By the way, it's kind of fun to see when he describes how he actually programmed tries. He says in the paper, the test program was written in Fortran for the IBM 709. The program is composed of 42 subroutines, of which 19 were coded specially for this program, and 23 were taken from the library. I mean, in Ed's last 30 years, the primary language that he used was Wolfram Language, our Mathematica language, and so at that point, he had, you could think of the functions of our language as being a very big library, and so he was able to make good use of that, very different from the IBM 709. Well, I should have set up to do this, because I did an interview with Ed in 2014, and I did a kind of a beginning of an oral history with Ed, and I recorded that whole thing, many hours of recording, and I should have thought that I could have actually played you that recording. Might have been fun, but let me tell you a story that Ed told me at that time, and he said, when he was talking about tries, people in the Air Force had no idea what he was talking about. And and apparently somebody said to Ed, there's a guy at MIT who does something similar. He calls it lists. And that person was John McCarthy. And you may know John McCarthy was the person who kind of used lambda calculus. Lambda calculus had been invented by Alonzo Church in 1935. John McCarthy tried to sort of use lambda calculus as a basis for creating programs for programming computers, and had developed, at least on paper, in theory, the idea of the language called Lisp, which was sort of based on lambda calculus. So Ed told me he arranges to go and see John McCarthy, and says, there's some guy wandering back and forth, and he says, "You John McCarthy?" John McCarthy says, "Yes." So Ed sort of says, "I've got this program, and could you take a look?" And as Ed told it to me, he said, then John McCarthy did something that struck me as very weird. He turned around slowly, started walking away. He's reading, and he's walking, stops, turns around, walks back slowly, and so on. Finally comes, he stops, and he reads, and Ed, as Ed told it to me, he's obviously very angry. And Ed says, I thought this is weird, doesn't make sense. He asks John McCarthy, does it make sense? John McCarthy says, yes, it makes sense. Ed says, well, what's up? John McCarthy says, well, I had the same idea. But according to Ed, John McCarthy said, but I've never written down the idea, so whatever. And so that's the story of how Ed met John McCarthy, and actually John McCarthy remained a friend of Ed's his whole life. I myself knew John McCarthy. I would say John McCarthy did not like Cellular Automata, I'm sorry to tell you. John McCarthy, when I was first writing about Cellular Automata, I sent John McCarthy this little paper that I wrote, like 4 pages long, and John McCarthy sent me back like a 6-page letter about why this paper and Cellular Automata were all irrelevant. It wasn't correct. It was very silly, actually. But I think John McCarthy had kind of didn't really like me because his language, Lisp, had been for a long time the kind of language of artificial intelligence. When I started building symbolic computation systems in 1979, it wasn't practical to use Lisp. There weren't really implementations of Lisp. And so I ended up just using C and building up my first symbolic manipulation program purely in C. And I think John McCarthy was sort of upset that I hadn't used Lisp for this, although he never really expressed that. His kind of upset came out in different ways. But anyway, Ed was a friend of John McCarthy's for a long, long time. And through John McCarthy, he met in the late 1950s another person in the Boston area involved with computers and later with artificial intelligence. Marvin Minsky was also a person I knew for many years, who I think I had a good relationship with for many, many years. So then there was another thing that happened in the kind of Boston computer scene, a company called Digital Equipment Corporation, which you may not have heard of, but for a long time it was the world's second largest computer company. IBM was the largest, Digital Equipment Corporation, DEC was the second largest. And they made a computer, their first computer was called the PDP-1. It was designed by a person called Ben Gurley. And Ed was responsible for buying a PDP-1 computer for BB&N. I will say that BB&N, Baranek Newman, it kind of got into computers as a result of Ed, and BB&N was also a critical company in the creation of the ARPANET, which is what turned into the internet. But this is Ed at the console of the PDP-1 computer sometime around 1961. And that was, computers in those days were much more stylish than they were today. They had lots of flashing lights and things like that. In any case, then Ed started working with a guy called Roland Silver. This is 1961. And Roland Silver and Ed were going to start their own company. They were going to break off from BB&N and start their own company. But they also were very enamored of the country of Brazil. Brazil had just elected a new president, and I don't know exactly what the politics of Brazil was at that time, but anyway, Ed and Roland Silver were like, the US is toast. We're going to move to Brazil. Brazil's the right place. And so they were just about to move to Brazil when this vaunted new president, who had promised change or whatever he had done, resigned. And so that scuttled their idea of moving to Brazil. But they initially were going to do this company together, Roland Silver and Ed. I never really got a straight story from Ed about why Roland Silver didn't end up doing the company with Ed. But it didn't happen. And I realized as I was talking to Ed back in 2014 or so about, no, actually even more recently than that, about Roland Silver, I thought that name Roland Silver, that's very familiar. I remember that name from somewhere. And I have a good archive, so I'm immediately able to look it up. And I realized that Roland Silver was somebody that I had interacted with in two completely different ways over the course of years. He'd been involved in symbolic mathematics, and also he made a thing, a strange magazine called Amygdala. And in addition to that, he made a thing called the Cellular Automatist. And so he published a magazine about cellular automata, Roland Silver, this is, together with a longtime friend of mine, Rudy Rooker, who actually I just saw a few days ago, who's a science fiction writer, among other things, also a mathematical logician. But anyway, Roland Silver, I found a rather nice thing in the Cellular Automatist, which he had sent me, I guess, back in the 80s. It says, Rollo Silver, the editor and publisher of the Cellular Automatist, is an ontological engineer who lives with his wife and works in the mountains of northern New Mexico in a house that looks like a flying saucer. Deprived of the company of his peers and half crazed by cognitive deprivation, he started the fractal newsletter Amygdala in 1987. So, and I later found out that Roland Silver was a college roommate of Marvin Minsky. So it's a smaller world than you might imagine. Okay. 1961, Ed quit his job at BBN and he had started a company. In 1957, he had met on a beach in Cape Cod, actually, a woman named Dorothy who he married, and very quickly, actually. And by 1961, they had a 3-year-old daughter. Ed had started this company. He'd sort of hacked the bank loans a bit, but eventually he was able to officially start a company called Information International Incorporated, III. Tiny office in Massachusetts, near Digital Equipment Corporation, which was also based in Massachusetts, and wasn't going too well. He was kind of trying to get consulting work from DEC and so on, and from BBN, but wasn't going so well. But then one day he gets a call from the Woods Hole Oceanographic Institute, which is a major US oceanographic institute in Massachusetts. And this is a story that he told me a version of years later, and I finally was able to sort of put the threads together. Okay, drives down to Woods Hole to visit this oceanographic institute with a person called Henry Stommel, who's an oceanography professor at Harvard, who tells him about a vortex ocean model and asks Ed if he can program the vortex ocean model on a PDP-1 so it displays ocean currents on a screen. Well, the result is that Ed says, sure, I can do that. And Woods Hole gives III a contract for what's now about $100,000 to go and do this. Now, years later, I was talking to Ed about the origins of cellular automata. And he told me at that time that a certain chap called Henry Stommel had told him that there were cellular automaton models of sand dunes from the 1930s. And I've never figured out quite what those models were. But this is kind of an early history of cellular automata, according to Ed, not always the most reliable teller of these things, that Henry Stommel, probably on that very drive down to Woods Hole, had told Ed about that cellular automata had been used as models of sand dunes in the 1930s. Anyway, well, I should speed up a bit in what I'm telling you, but the thing that Ed did for Woods Hole was particularly to get a computer to read film. They were recording data on photographic film, and Ed, this is a patent, Ed's, I think his first patent, no, actually, Ed's first patent was a mechanical device, but this was an electronic device. You can see kind of the lenses and things. This was for reading film and digitizing, turning to digital form what was visible on the film. Okay, so, and that idea of film reading just had a ton of applications, and in fact, kind of really fueled Ed's company, III, for many years. So this was a paper that Ed wrote, Computer Compiled Oceanographic Atlas, an experiment in man-machine interaction, together with the aforementioned Henry Stommel. And what they did was, well, it had various statements in it. Only a high-speed computer has the capacity and speed to follow the quickly shifting demands and questions of a human mind exploring a large field of numbers. And in that paper were visualizations. These are visualizations of oceanographic data on an oscilloscope gotten with by digitizing film. So, okay, the a couple of years later, Ed moves the company from Massachusetts to Los Angeles, near where he'd grown up, and also near where the SAGE project that I mentioned earlier, this Air Force project, had kind of moved its headquarters. So Ed had lots and lots of ideas for III, and he brought in Marvin Minsky and John McCarthy as board members and consultants, and actually was doing things like in 1964, proposing to make a new version of Lisp, and doing all kinds of different things. In 1964, III had 4 divisions: mathematical and programming services, behavioral science, operations, and one called New York. So, you know, an example of what III was doing, remember, III had been started as, its first business had been making film recorders. But it was also, there were people at III working on inductive inference on sequences. That's kind of things like Ray Selmanoff's work and Greg Chaitin's work on algorithmic information theory, talking about this as in terms of Lisp functions and so on. This is sort of an early example of machine learning, of essentially a language model, but it's a very simple language model. Now we have LLMs that have a much more sophisticated version of this. And III's business grew, and perhaps in some ways it outgrew Ed. In 1965, Ed stepped down as CEO of III. In 1968, he left entirely and went to MIT. I'll describe how that happened. Well, I talked to Ed quite often about his history with companies. In fact, back in 1982, Ed had kind of wanted to make a deal with me. His deal with me was I would teach him how to write an academic paper that people would read, and he would teach me how to start and run a company. I wasn't very convinced by this deal because I'd already started my first company a year or two earlier than that. And I wasn't sure that Ed was really set up to be a writer of academic papers. So that deal never really happened. But I asked Ed a bunch about sort of his life and times with companies. And he always told me the thing that went wrong with his first company is that his partner had died. And I thought, well, they got it started and they were partners and then the partner died. But when I was writing the obituary for Ed, I found out what the actual story was. The actual story was that after Ed set up III, he'd persuaded Ben Gurley, who I'd mentioned earlier, who was the designer of the PDP-1 computer, to leave DEC and join III. And really, Ed's plan had been to build computers at III. He wanted to go into competition with DEC. He wanted to be one of the world's big computer companies and design computers. But Ben Gurley was sort of the top computer designer of the time, and Ed had recruited Ben Gurley. But on November 7th, 1963, Ben Gurley was murdered. And somebody shot him through the window of his house. And actually, bizarrely enough, he lived in Concord, Massachusetts, which is the same town that I live in. And I looked up the details of this, and Ben Gurley lived a few miles away from where I live. And Concord, Massachusetts is not the kind of place that has lots of shooting of people going on. But in any case, the story of Ben Gurley, I think I have some. Oh, maybe I didn't put it in the piece that I wrote. But it was a kind of a weird situation where there had been an engineer, a digital, who had kind of gone off the deep end, and that was the person who ended up killing Ben Gurley. So that was the story of why Ed didn't get into the making computers business. There's a little bit more history there, but it's not so relevant. Okay, so anyway, so Ed by 1965 had kind of was winding down from III, and 1960, but he was still its chairman. And in late 1968, something happened that would sort of change Ed's life forever, which is he took III public. And so, I mean, Ed told me a few more details of this, which I'm not sure I put in the piece that I wrote. But Ed had a broker who offered to take III public, and this is the public offering. Well, this is a report of the public offering document, Information International Incorporated at 545 Technology Square, Cambridge, Massachusetts, filed a registration statement, blah, 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 blah. And it said the company has outstanding 2.3 million shares, of which Edward Fredkin, board chairman, owns 57.7%. So, and the Ed Fredkin Charitable Foundation owns 0.4%. So, January 8th, 1969, III goes public, and Ed, at least on paper, is suddenly worth $10 million, which is the equivalent of about $80 million today. And 2 years later, probably when a lockup period expired, Ed cashed out, and Ed had done something which is now somewhat common as well, which is he borrowed against his shares in III, and so a lot of but anyway, he basically cashed out $80 million. So Ed was 37 years old at that point and had made a bunch of money. And basically the money he made from III would last the rest of his life through a series of rather unsuccessful business ventures, which I'll describe because they're kind of interesting. III had tried to do an OCR project that hadn't really worked out. Eventually, III had gotten into the business of making computer-generated special effects that made it into movies like Star Wars and so on. And it made systems that went from digital to film and from film to digital. Eventually, when PostScript came out in 1996, though actually PostScript came out earlier than that. Well, PostScript was out in the late 80s. But PostScript kind of removed the market for what III had been doing. And eventually III was sold to a company called AutoLogic that makes typesetting machines for a fairly modest amount of money. Okay, when III went public in 1969, it was the height of the Cold War, which didn't hurt the fact that III was selling a lot of film scanners to the US military. So in 1969, many people, I don't know about in India, but many people in the West, in places like England and so on, thought World War III might be right around the corner. And so in 1970, Ed decided to buy an island in the Caribbean that was close enough to the tropics, he told me subsequently, that actually incorrectly, according to current models, radioactive fallout from a nuclear war wouldn't reach that part of the Earth's atmosphere. So according to Ed's later wife, Joyce, Ed was sitting in a dentist's office when he saw an ad in a magazine that said "Island for Sale," and so he decided to buy the island from a kind of a rather colorful chap who was often characterized as the last pirate of the Caribbean. But anyway, Ed bought this island, 125-acre island in the British Virgin Islands. Its name is Mosquito Island, which is a bit of an unpromising name, although Ed tried to usually spell it with a K rather than a QU to not remind one of the little critters. Anyway, it didn't cost much when Ed bought it, probably under $1 million. Subsequently, Richard Branson of Virgin fame bought a nearby but smaller island, and actually Ed eventually sold his island to Richard Branson many, many years later. Okay, 1982, when I met Ed. I first met Ed on his island, and you kind of approached the island in a boat, and I don't know, it reminded me a lot of these James Bond villain islands of, you get there and there's somewhere you can see, I think in this picture, you can see as you approach the island, there's a plane there. This is, Ed had developed a kind of the island into something of a resort, Drake's Anchorage, he called it. I don't know whether Francis Drake ever actually went there, but in any case, this was this is his island that had a little bit of a resort on it. Now, these are pictures that I took when I was on the island. This was a rather pleasant beach on the island, which I was not that into, but was a beach nevertheless. And that was Ed's plane. It was Ed's plane, just a seaplane. Let's see if I can make that bigger. It was just a picture I took of Ed's seaplane, and I, in fact, as it happened, right at that time, I had just learned to fly small airplanes, and so I was kind of into, hey, can I fly the seaplane? And you can't just go off and fly a different kind of plane than you've flown before, but I was flying it with somebody else. And this was a picture that I took from the seaplane, of Ed's island, and that was the one house on the island was there, and that's Ed's island as of that time. It was kind of interesting. Well, there aren't very many pictures from that trip. I mean, there are pictures that I took. This is one picture I think somebody else must have taken because I'm in it. That's the younger me there, and that's a chap called Charles Bennett, who you might have heard of because he's done a lot of stuff. He did a lot of stuff in reversible computing, and then he was sort of one of the first people to point out that you could have a reversible Turing machine. Subsequently, he did a lot of work in quantum computing and quantum cryptography, particularly. Well, people often talked about Ed and his island, and there was sort of the whole island projected a mystique of, general mystique and sort of a high wealth kind of picture. In 1983, there was a movie called War Games that came out, which you might have seen, that featured kind of a reclusive, military-oriented computer expert named Professor Falcon, who had an island. And many people assumed that Falcon was based on Ed Fredkin, and it says that all over the internet. But and Ed himself believed that. He'd never actually done the due diligence to check it out. But when I was writing this obituary for Ed, I happened to have contact with one of the writers of the movie, of the War Games movie, a chap called Walter Parks. And so I asked him, was Ed the motivation for this character? And he says, unfortunately, I can confirm that Ed was not the inspiration for Stephen Falcon. The character was inspired by Stephen Hawking. Falcon equals Falcon equals Hawking. The movie was first conceived to be about two characters, a young super genius born into a family incapable of acknowledging his gifts, and a dying scientist in need of a protege. In the first several drafts, Fredkin was confined to a wheelchair and was working on understanding the Big Bang, for which he had created a computer simulation. Little known fact, according to Walter Parkes, is that while writing the character, we had one person in mind to play the role, John Lennon, who was murdered shortly before we finished the script. So, you know, in a case of fact follows fiction, War Games had this computer in it that had lots of flashing lights. And many, you know, when War Games first came out, I happened to see that movie with a person called Danny Hillis. And as we were walking out of the movie, well, Danny Hillis had been a student of Marvin Minsky's and had started a company called Thinking Machines Corporation, which made a parallel processing computer with 65,000 processors in it that was actually ideal for simulating cellular automata. And I did a bunch of work on that computer with cellular automata. But as we were walking out of seeing the War Games movie, I said to Danny, you know, perhaps your computer should have flashing lights as well. And indeed, I'm sure I can find quickly a picture of the connection machine. Indeed, the connection machine, its big feature was that it was covered in flashing lights. And in fact, I think it later showed up in all sorts of, let's see if I can quickly find a picture. There we go, that's a good picture. See if I can pull that in here. Is that gonna work? There we go. Come on. Okay, that's a rather blurry picture of the connection machine computer covered in flashing lights. That was kind of a fact follows fiction story that came from the War Games movie. Anyway, 1968. Ed has left III. He ends up joining MIT, specifically a thing called Project Mac, the multiple access computer, the first time-shared computer system, really. Ed was sort of an expert on the time-sharing, 2 words, of computers. This is by Edward Fredkin of Information International. And there's the computer input device that you can see, a teleprinter. It's kind of fun to see the kind of a short history of time sharing. In the 50s, it was clear that to many people that, one, computers would eventually think. The main problems would lie in knowing what to do and how to do it. Computers would help us do it. That doing what we decided to do would be a programming task. The computers would help us do the programming tasks, and that we needed systems and languages that allowed us to use the capabilities of computers to the extent of our needs. It's kind of a similar story to what we might say in about AI today. And in any case, it's kind of fun to see the magazines of that time, kind of the ads and so on. There's a typical computer of the time with a built-in desk and all those kinds of things. Anyway, Ed kind of became an expert in time-shared computer systems. This is a picture from his work in oceanography, actually. I think that's in oceanography, that's vortices. This is kind of an interactive computer screen showing some Lisp, showing kind of symbolic computation there. Okay, well, we've got all sorts of things. There's an interesting piece here. Okay, I'll just look at this. This is from 1968, I think. A big picture of the far future. If we assume that the development of artificial intelligence will take place, how can we form a coherent picture of our place and its place in the great scheme of things? It seems reasonable, Ed wrote, to consider that artificial intelligence is a next step in the evolutionary process. Once there was a prototype land creature that crawled out of some primeval ocean, most primitive in comparison with a more advanced creature such as the saber-toothed tiger. And once there was a prototype intellectual creature, that's us, and we will seem most primitive in comparison with what is to come. However, instead of participating in evolution by merely serving as a runner in a genetic message relay race, we can choose the great distinction of directly employing our primitive yet unique intellectual talent for the task of evolution. We have conceivably arrived at the notion of the next step in evolution by trying to fit the future development of artificial intelligence into the overall scheme of things. Joshua Lederberg, chap I knew actually, a Nobel Prize winner and geneticist at Stanford University, gave some attention to the problem of guessing the characteristics of that species that will evolve from mankind. He arrived at the conclusion that it would be artificial intelligence. How do we proceed with this great task? J.C.I. Licklider's position in 1959 was that we should concentrate on the development of man-machine symbiosis, a system in which men and machines, sorry, it was not people and machines yet then, would form a close-knit intellectual team. By the way, having said that, most programmers were women at that time. So even though it says men and machines here, it's a bit of an unreasonable thing. Anyway, would form a close-knit intellectual team, each complementing the capabilities of the other. Then, when so equipped, we could much more effectively tackle artificial intelligence. After the ascendancy of AI, it seems that mankind's intellectual skills will no longer be very useful in the solution of problems. Today, man is hardly using the intellectual capability he has. How ironic it would be to pass through our span as the dominant species in the Earth's evolutionary tree without ever realizing our true potential for intellectual creativity. By means of a symbiotic relation with the capabilities that we now know how to implement in computers, we can not only proceed with the task of creating AI, but we can reach for and achieve human creativity at a pace and level never before attained. We could advance all areas of science and art as partners in intellectual systems that complement and reinforce our correctable weaknesses and that make use of all our inherent creativity. With computable wings, we could soar to meet the phoenix. It's kind of cool. Ed wrote that 60 years ago. And much of it is with slightly different characteristics we could write today. Okay, curious piece of history, 1961. Ed even wrote some of this history down. Ed and Marvin Minsky are visiting, John McCarthy is looking for a job because John McCarthy had not gotten tenure at MIT and he was traveling around looking for a job. John McCarthy had been an undergraduate at Caltech and was sort of interviewing at Caltech for a job. He didn't end up going there. He ended up going to Stanford instead. But they were kind of hanging around and apparently Ed suggested that they meet somebody interesting. And I'd remembered Linus Pauling, famous chemist from his time at Caltech, but Pauling wasn't in. So Minsky suggested they call Richard Feynman. He was in and invited them over to his house. And apparently they spent a long time. Ed told me a lot of detail about his interaction with Feynman that very day. But one of the things that Feynman talked about was the problem of symbolic integration and the problem of doing algebra by computer. And he describes this whole 50-page calculation that's got different answers and so on. He wants a computer to be able to do it. Okay, so the original proposal for Project Mac was based on the idea of doing mathematics by computer. So the very term Project Mac was either multiple access computer or it was project on mathematics and computation. Well, it ended up that Project Mac was funded and there started the development of this mathematical computation system that eventually became a system called Maxima, which was an early computer algebra system. Well, a few years later, so that was kind of being completed by the early 1970s. A few years later, 1976 actually, when I was 16 years old, I got access to the ARPANET, now the internet, and I was able to connect to this computer at MIT. And a few years later, this is what, I don't have a printout from the very beginning of doing it, but this is what it looked like to connect to going through the RAND terminal interface processor, which was the interface to the internet. Open port 236. That time, all the nodes on the internet were numbered. There were 512 of them, and 236 was this computer at MIT. So you reach the computer, the Maxima Consortium, KL10, that's a digital equipment computer, and it's got this message of the day describing about different kinds of users. It's like, welcome to the operating system. There it is. It looks very modern. And I guess this is, there's the date there. Anyway, that was kind of that story. Well, anyway, Ed can tell more about Ed at MIT, Ed was had never gotten a college degree. He dropped out of college after the first year in college. I don't think he ever learned calculus, for example, which will be a problem for him subsequently when he tried to study physics. But Ed was a very popular, lively kind of professor at MIT, and he taught a problem-solving course at MIT. And I looked at his archive, and I found all kinds of interesting notes that he made for himself. Lecture number 1: what is power? What can be done with money? How is it done? How is it done in the Soviet Union? How do we do research? These were the kinds of things he was talking about in his lectures at MIT. This is a picture of this, I think, 1968. This is a picture of, I don't know if you guys can recognize any of the characters here. That's Ed there with, that's John McCarthy, creator of Lisp. That's Claude Shannon of information theory fame. And that's Joe Weizenbaum, the creator of the ELIZA chatbot, the first chatbot, sort of the ChatGPT before there was a ChatGPT, so to speak. In any case, in 1968, Ed kind of ended up staying at MIT. He might have left there, but he stayed, and he became the director of Project Mac. And he tried to make some sort of definitions, like what is a bit, what is a word, what is a register, these kinds of standardized definitions about things. He also participated, there was a thing called HackMem, which was this kind of collection of kind of interesting factoids, a few cellular automaton ones in it, but there are a couple attributed to Fredkin, like 3 cubed plus 4 cubed plus 5 cubed equals 6 cubed, and a result about Pascal's triangle-like thing. Yeah, actually, a notable thing that came from my friend Bill Gosper is the Munching Squares algorithm, which is a kind of very cellular automaton-like algorithm. Anyway, right around that time, 1970, was when the Game of Life cellular automaton kind of came online. And Bill Gosper at MIT was very deeply involved in that, discovered the glider gun, things like this. Ed Fredkin was right there at MIT, but doesn't seem to have ever interacted with the life hackers. Instead, he was doing things with his problem-solving course, and he formed a group called the Army to End the War, which at that time was the Vietnam War for the US. And it was a whole scheme to stop the government fighting an unwinnable war, in which he would have an organization that would coordinate citizens to threaten a run on banks unless the war was ended. But it didn't work out that way, and didn't really fit very well with Ed's project being funded by the US Department of Defense. Well, lots of strange things would happen. This is a chap called Patrick Gunkel, a long time kind of I would say a protege of Ed's. I met Patrick Gunkel a couple of times. One time I met him. It was notable. He lived in a small town on Cape Cod in Massachusetts, and Patrick Gunkel would ride around town with his cat in his bicycle basket, which made for an interesting spectacle. But Patrick Gunkel was a kind of a wild character, but this was a kind of a typical Ed Fredkin, Patrick Gunkel kind of story on the theme of the conception of a mechanical civilization in the next century, that's our century, and beyond. The dense and colorful conversation will twistingly navigate human potentiality, finiteness, liability, and aspirations, etc. Anyway, Patrick Gunkel was interested in the thing he called ideonomy, the science of ideas. Okay, cellular automata. So, the thing that Ed had sort of hatched the idea that the universe will be a giant cellular automaton. Ed believed he was the world's best programmer. He thought he can program anything, including the universe. He could make a cellular automaton that would be the universe. And apparently he told this to John McCarthy, and John McCarthy says, well, if that's the case, why don't you look for round-off error in the behavior of the universe? And Ed was like, John McCarthy doesn't get it. He thinks it's an IBM 709 computer in the sky. really, it's just the bits of a cellular automaton that Ed thought would be the universe, so to speak. Now, actually, in truth, when we look at our physics project today, and we look at kind of how you might detect the discreteness of space, John McCarthy's idea is not quite so far off. But in any case, Ed had told me, I had talked to Ed in the mid-1990s when I was writing a new kind of science, and Ed had told me the following story, that in 1961, he simulated a 2D analog of Rule 90 on a PDP-1 computer and noticed its self-reproduction properties. That's what Ed had told me, and he told me that fairly convincingly, and turns out it wasn't quite true. But in 1969, looking at his archives, the 1969, he wrote Thinking About New Things. And the purpose of this paper is to plant a notion in the minds of today's physicists and philosophers about new ways of thinking about things. So that was actually when he started thinking about computers as a way of modeling the universe, was 1969, not earlier than that. And the story about John McCarthy was 1959, but the idea of he starts talking about sort of interactions of particles and so on, and then eventually he talks about this idea that the universe, as that compares it to a computer simulation, has attractive features. However, it is really sort of absurd to think of the giant IBM in the sky. IBM was the biggest computer company at the time. Needless to say, there are many unattractive features, aspects, major flaw, it is hopelessly contrived, etc., etc., etc. Gravity might be a rounding error of some kind. He talks about these things. Okay, later on in this document, 1969, Ed is beginning to get to the idea of cellular automata. One of the advantages of a digital or discrete model of physics became more apparent to me as I began to think of simpler ideas and mechanisms. If such a model could be developed, then algorithm involving bits of information would become the basic ingredients of all the processes we observe. We would be able to achieve a total and complete understanding of the nature of the most basic aspects of physics. The reason for this is that the idea of a finite state automata is exact and easy to understand. It is a process that involves information in a simple yet precise way. Let us consider a simple automata, which I will refer to as a cell. The cell has exactly two internal states. Unlike a complex thing such as an atom, which can be in many states, our simple cell will have just two, etc., etc., etc. And so then he goes and he describes, let's see, if such a cell is not very interesting by itself, he says, however, if we arrange a large number of them in some orderly fashion, then interesting things begin to happen. Let us say we make a space up of a Cartesian lattice of points. Each point would have exactly 6 neighbors, unless it was an edge or a corner. We can think of it as up, down, north, south, east, and west. He's thinking of it in 3 dimensions. We imagine such a point in a very large space of points. Then the inputs, blah, blah, blah. Okay, he has a lattice, and so on. And then he describes this as a spatial automata. That's a spatial automata is certainly one of the simplest structures that one can imagine that is capable, as we shall show, of exhibiting very complex behavior, or what he describes as very complex behavior. Okay, at this point, he thinks he's almost reproduced physics. Well, the rule is only the specification necessary to explain the behavior of such a machine, only 2 numbers, blah, blah, blah. He's talking about clock rates and ticks of clocks and things. And now he's trying to enumerate possible rules. So this is, and look at that. He says if a rule has 7 inputs, then there are approximately 3 times 10 to the 38 different rules. This is 2 to the 2 to the n, where n is 7. And then he's saying, let's look at the definition of these rules. It's very cellular automaton-ish. He's kind of, it looks like he might be doing the kind of thing that I did in the 1980s, but he's not. His approach is very different. He's not doing science. He's not studying these rules and seeing what they do. He's trying to design a rule that will be the universe. he's trying to be an engineer, a programmer, and program the cellular automaton. So here he's saying summary of the 8 rules. So these are rules. This is just like an elementary cellular automaton, but now he's got kind of an interpretation of these different bits in the rule. That's a left shift, that's a right clear, etc., etc., etc. He's giving a kind of a programmer's interpretation of all the bits in the rule. And he never simulated these things. If he had, he would have done the same things that I did in the 1980s. He would have started with these particular rules. He would have started seeing pictures like this, but he never did that. Even though he had worked on graphical representation of computer output, he never simulated these cellular automata. He only, even though he sort of themed himself as the world's best programmer, he only wrote down what cellular automata would do. He never actually ran them on a computer at that time. So he discusses sort of results about sort of theorems about data processing with cellular automata, but he never looked at these. And actually, it's sort of interesting. I found this in Ed's notes in the archive, in Ed's archive at MIT, which actually even his wife didn't know existed. But but even though he actually had worked on one-dimensional cellular automata, but in all the years I knew him, he never once mentioned one-dimensional cellular automata to me. Anyway, so later on, he gets back to kind of just how spatial automata might model physics. And it's kind of a hokey story of electrons and exclusive ores and things like this. It's really trying to construct physics as a programmer, so to speak. And he has, you know, things like he has a models for particles. It's my conjecture that the models for particles will consist of fairly elaborate structures that represent momentum by means of some function of the length and orientation of spiral arms. Let us consider a particle capable of moving slowly in any direction. Imagine that it has 3 spiral arms. Each arm emanates from a central region and is shaped like a ribbon. Each ribbon is wound up, intertwined with other ribbons, each of the 3 ribbons being wound up around an axis that lies along a coordinate, etc., etc., etc. It's a very mechanical model of what physics might be like underneath. Oh yeah, he also discusses the possible design of a simulator to sort of make a computer, 1,000 by 1,000 by 1,000 3D grid of cells that he estimated could be built for what would now be about $500 million. Well, in any case, the I've tried to trace more of this history. But one of the things that happened around 1969 is that Ed got convinced, probably by Marvin Minsky and John McCarthy, that any cellular automaton capable of being the universe better be computation universal. And so that led him to get a person called Roger Banks to write a thesis about cellular automata. I don't know how much Ed really interacted with Roger Banks. Later on, he would describe Roger Banks as his student, but I think Roger Banks may have been, interacted more with Terry Winograd, another professor at MIT. And I think at the end, let's see, this is the supervisor, this is the acknowledgements, the only thing people actually read in theses, I think, sometimes. I wish to thank Professor Edward Fredkin, supervisor of this thesis, for introducing me to the topic of cellular automata and providing expert supervision, especially pertaining to the direction which this investigation has followed. So I don't know exactly what the involvement was there. But in any case, yeah, I think so that was sort of Ed meets, does things with 2-dimensional cellular automata. Okay, this is now my sort of interactions with Ed starting 1981. Like to invite you to a workshop on information mechanics to be held on Mosquito Island in January 1982. And then keeps going and so on. What did I find on that island? What I found on that island was at that time, Ed had invested in a company called Three Rivers Computer Corporation. Three Rivers Computer Corporation had built a computer called the PERC, which was an early workstation computer. And Ed had one of these computers shipped to the island. The island had 100% humidity. Electronics does not, as I suspect some of you may know well, electronics does not generally mix well. Modern electronics is different, but more discrete electronics does not mix well with 100% humidity. So it was a hell of a time getting the PERC to operate properly on the island. Let's see if I can pull this image in here. See if that works. No, I think I have to show that to you separately here. Hold on one second. Okay, so what did Ed have running on the PERC? This is what he had running on the PERC. It was, let's see if okay, there we go. This is a reversible cellular automaton. And it starts from, and Ed wanted to show me this kind of behavior of the reversible cellular automaton. All happened rather quickly. It was kind of hard to see what was going on, but you know, Ed was pressing buttons and the display was doing these kinds of things. Now, what that was in many ways, Ed viewed it as kind of a display hack. This is something that Bill Gosper gave me. It's actually a printout from the very first color laser printer from 1979. And it was kind of a display hack done by Bill Gosper at Xerox PARC. Anyway, Ed showed me this display hack on the PERC computer. And then Ed handed me a floppy disk. And I'm a good keeper of archives. I still have the floppy disk today. You can see it's a very big floppy disk. If any of you, some of you have seen the floppy disks, the 3.5-inch floppy disks that people use. This was an 8-inch floppy disk, big floppy disk. Anyway, there was a, I'd never read what was on this floppy disk. We went through a whole adventure with the Computer History Museum to try and read this floppy disk. Fortunately, I had a printout of some of it, and I think we verified that what was on the floppy disk was what was in the printout. This is the printout. It's a program written in Pascal, and it is a program, CA1, input-output. This is a program for running cellular automata, or maybe it's running cellular automata, because what it's actually doing is bitmap operations on the display screen. These are raster ops on the display screen. And so there are, it certainly seems like it might be about cellular automata because the function is called CA1. And you'll see, you know, there are very few comments in the code. There's one that is a random number generator that's a feedback shift register random number generator in this code, and so on. There's help text. There's a little bit of help text here. And one of the things it says is press P for the EF1, Ed Fredkin 1 rule. Press B to clear the cellular automata boundary. Okay, so this is, so we can run this program now. We did run it. And if you press one of the keys, you get this pattern. This is a two-dimensional, reversible, additive cellular automaton. I think Ed showed me that. I'm not sure if he showed me that, but he was much more interested in showing me these much more complicated patterns and showing that you could reverse them, that you could run them forwards and you could run them backwards, and they would reverse things. Now, and that was kind of, now, when I was on the island in 1982, one of the other things that was there was this object. This is a picture I took. I'm afraid it's a bit out of focus. That's what you get for a film camera. This was a machine. You can see it's a discrete component. It's the breadboard there. This is a machine made by Tom Toffoli that was a hardware cellular automaton simulator, a hardware 2D cellular automaton simulator, and a cellular automaton machine. And actually, I found, looking at the negatives of the pictures, when I was making this, writing this obituary, I found this picture. This is actually a picture made with a hardware cellular automaton simulator of a 2D cellular automaton. I don't know if it's a reversible one or not. I don't exactly know what rule this is. But that was something that I photographed from that hardware cellular automaton machine in 1982. Well, we can talk about. So there's. Let me say a few more things about Ed. Gosh, there's so much to say, but and maybe I shouldn't go on too long. But I can talk about the interaction between Ed Fredkin and Dick Feynman. A lot of strange interactions. I mean, Dick Feynman, who I knew pretty well, always liked unusual characters, and Ed was an unusual character. And somehow Ed was trying to Dick Feynman had a friend who was making a machine for cutting cloth, and he was trying to get Ed Fredkin to help him with the commercialization of this machine for cutting cloth. So that was a strange sort of piece. But more interestingly, at a time, and I was already in the picture at this point, in 1980, Feynman was writing to Fredkin about billiard ball computing. This is sort of reversible computing, and Feynman was trying to figure out, Ed had been having this idea about reversible computing with billiard balls, and Feynman was trying to figure out sort of how that would work. And that's where he named something the Fredkin gate. I think it was Feynman who named it that. And nowadays in quantum computing, one talks about Fredkin gates, and they work exactly this way. I don't know whether Fredkin, I think Feynman may have been the one who actually wrote down the specification of this thing that now is called the Fredkin gate. And that was the handwritten page that I found from the Fredkin archive at MIT of this. Now, Feynman, I talked to Feynman at length about things to do with, he always viewed Fredkin with a little bit of a sort of apology for being, he thought Fredkin was kind of a nut. And, but he found him lots of fun. Actually, Fredkin had often told me that he kind of convinced Feynman that sort of to take seriously the idea of space, of the universe being a cellular automaton. I don't think Feynman ever took that seriously. He didn't really believe in that. But Feynman did in 1964 already start talking about, it always bothers me that according to the laws as we understand them today, it takes a computing machine an infinite number of logical operations to figure out what goes on in no matter how tiny a region of space and no matter how tiny a region of time. How can all that be going on in that tiny space? Why should it take an infinite amount of logic to figure out what one tiny piece of space is going to do? So I have often made the hypothesis that ultimately physics will not require a mathematical statement, that in the end the machinery will be revealed and the laws will turn out to be simple, like the checkerboard with all its apparent complexities. But this speculation is of the same nature as those other people make. I like it, I don't like it, and it's not good to be too prejudiced about these things. So, well, there's a whole story about Ed and sort of his feeling that Feynman had sort of ignored what he told him, and there's a bunch of stuff about that. But anyway, Ed sort of was keen on this idea of digital physics. He taught a course about digital physics at MIT, and he had various notes from that. Ed was always keen to tell me the story that a person called Al Meyer, who's still alive, who was a computer science professor at MIT, had told Ed that the field of cellular automata was dead by the mid-1970s. And in fact, more particularly that Al Meyer had said to Ed that one can tell someone is out of it if they don't think cellular automata are dead. So it's an irony that I pieced together that Al Meyer's future wife, a woman called Irene Greif, another computer scientist, would point a longtime friend of mine named John Mazuris, who actually we'll meet later in the story, perhaps if I get there, would actually point Irene Greif, who would later be Al Meyer's wife. Al Meyer had described that cellular automata were dead, would point John Mazuris at Ed and his work on cellular automata. Well, anyway, Ed's ideas about physics weren't very well received by people at MIT. Philip Morrison, well-known physicist, asked what he thought of Ed's approach. He responded, "Of course, Professor Fredkin thinks the universe is a computer. He's a computer person. If instead he was a cheese merchant, he'd think it was a big cheese." So in any case, there's a lot that Ed ended up doing with reversible computing. He interacted with Carver Mead, who was an early silicon compilers person. This is something which I found this in Ed's archive, and it's like, what is that? Well, I then found this picture in Ed's archive, and I don't know if you guys can identify what that is. I don't know if anybody knows what that is. To me, it's I immediately knew what that was. It's a sorting network. It's actually the optimal sorting network for, I guess, a size 16 sorting network. It wasn't original to Ed. It was discovered that this is a particular sorting network discovered by a guy called Milton Green in 1969. But Ed was clearly thinking about sorting networks, which are reversible computational systems back at that time. Let's see. Well, there's a lot on reversible computing, circuits, and so on. Here's another thing that Ed was very interested in. Well, this is something that Marvin Minsky figured out, that you could make an approximate circle by using that little piece of code there. That by with these sort of, you could make that thing that would be nearly a circle. It isn't quite a circle. And in fact, as you change the parameters, it becomes not much of a circle at all for many choices of parameters, but it's kind of a hack for making a circle. Now, later on, Ed would find that very significant, that you could make this approximate circle, and he would tell me much later that he kind of discovered the electron because he could get these kind of circular paths. Just to fill in a few other things, perhaps of interest, 1981, Ed organized a conference about the physics of computation. I was going to go to this conference, and I didn't end up going in the end. But this conference has a good collection of many people who were kind of figures in kind of computation, some cellular automaton people, and so on. I could describe the stories of many. Well, there's Art Burks, number 35. Art Burks, who I knew was the person who invented the term cellular automaton. And there are a whole bunch of other cellular automaton people in that picture. Well, in any case, another thing that was at that time, Konrad Zuse, the person in that picture, Ed kind of got to know him. I exchanged letters with Konrad Zuse. I met Konrad Zuse's son. I can tell you a whole bunch of stuff about Konrad Zuse and cellular automata, and actually not really cellular automata, more kind of discrete space, but continuous variables. In any case, so Ed sort of was talking about cellular automata. He talked about many, many different kinds of things. So he had the idea, this is an example of another idea of Ed's from 1976, a thing called the Intermon unit of exchange. This was kind of a Bitcoin before there was Bitcoin kind of idea of a new kind of currency. And he would have other ideas. This was an idea that he had with Marvin Minsky. This is actually another cellular automaton story. This is a thing called the Muse, the Triadex Muse. And that's a patent application for the Muse. This was a cellular automaton music generation system, and which I've seen and played with. It kind of was it was basically a linear feedback shift register, an additive cellular automaton for making music. It makes rather strange sounds. I think maybe I had a version of this sound. And then, Ed did things like he put up a prize for the first computer to beat a grandmaster at chess, and he put up an AI prize, math AI prize, which has never really been won. Ed also did a whole bunch of consulting for companies. He has all sorts of interesting stories about his life and times working with people at IBM and so on. He also was trying to do a bunch of companies himself. He tried this Three Rivers Computer Corporation. There was the Triadex Muse. He had another Ed Fredkin thing was a company called, it was called something water, Reliable Water, that's right. This was a company, there's Ed on the left there. This was a company for making reverse osmosis, or turning seawater into drinkable water, relevant if you have a tropical island. Ed always told me when he did this, he was like amazed. He had these reporters come and drink water that had been purified from Boston Harbor, and they all happily drank this water. And he was like, they were very trusting to do that. But this was Ed kind of trying to use sort of AI, as he sort of described it, to yeah, it was in those days the sort of the AI idea was kind of expert systems were a kind of typical name for these things. There's Ed with his intelligent desalination system with a bunch of weird tubes and things that had valves controlled by computer. Also, another bizarre thing that happened with Ed is he ended up owning a television channel. And it was sort of a strange story of a television channel in Boston. This is actually the agreement. This is 1982. This is, I photographed this from a shelf at Ed's house. This was the strange story of the purchase of New England Television by Ed Fredkin. And it was a whole story because it was kind of in the US, you have to sort of you had to convince the government that you were sort of a responsible person able to run a television station. And there was a big fight about whether Ed was really a responsible person who could run a television station. But anyway, lots of wild things there, and many, many inventions. This was an invention for an automatic refueling station for cars. You can see the refueling thing kind of, I think probably the idea came from airplanes. Then he had ideas for automated contract systems and traffic negotiation, and he had kind of a this was a self-driving car before there were self-driving cars, with some kind of whole scheme for the cars to interact with each other. Lots of different things. Now Ed also Ed was very much into planes. He had a variety of planes. They were always registered with a tail number N1EF. N is the designation for a US-based plane. 1EF, EF for Ed Fredkin. So he had jets. He had all sorts of other kinds of planes, and he had many stories about planes and the adventures with planes, which maybe I won't talk about because they don't really have much to do with cellular automata. Okay, I have to tell you about one or two other sort of Ed features. Another was the story of Ed and the Soviet Union. So, ironically enough, John McCarthy, his parents were active communists. Now, you may know about McCarthyism in the 1950s in the US. That was not this McCarthy. That was an unrelated McCarthy who was a senator. But John McCarthy had very communist roots. And so McCarthy came to Ed one day and said, I'm moving to the Soviet Union, and planned to renounce his US citizenship and so on. And that was 1968. And if you know the history, that was when the Soviet Union invaded Czechoslovakia. And John McCarthy apparently sent a telegram to the leadership in the Soviet Union saying, if you invade Czechoslovakia, then I'm not coming to the Soviet Union. And as Ed told it to me much later, if the Soviets were really understood things, choosing between Czechoslovakia and John McCarthy, they should have chosen John McCarthy. Later in his life, John McCarthy would absolutely flip his political opinions and become a staunch conservative, but that's a different story. Anyway, Ed Fredkin started traveling to the Soviet Union. You can see in his archives various things about surveys he was doing about what it's like to visit the Soviet Union. This is now a conference on AI in the Soviet Union, 1977. This is the International Meeting on Artificial Intelligence in Leningrad, what's now St. Petersburg. 1977, theories of knowledge representation, blah, 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 computer game playing, mathematical aids to machine aids to mathematical reasoning, and so on. And the various non-Soviet contributors include Ed Fredkin, John McCarthy, Donald Mitchie, et cetera, et cetera, et cetera. So, and this is now a picture of Ed at that conference. There's John McCarthy, there's Ed. Note everybody's wearing headphones because that was a booth back there for a simultaneous translator. That was sort of typical in conferences at that time. Well, there's a whole long story of Soviet Union and Ed's interactions with that. This is a letter that Ed wrote to, I guess it was sent to US president. It was about a concerned citizen of planet Earth. The world is rapidly plunging towards a terrible fate, et cetera, et cetera, et cetera, in 1984. Now, somehow in the middle of this, Ed got involved in a strange negotiation associated with the person called Andrei Sakharov, who was a Soviet physicist who I never met, who was involved with the Soviet nuclear weapons program, but was a Soviet dissident and wound up being sent to Siberia. And there was a whole big production about that in the West. Well, Ed, by this point, was trying to arrange to get PCs to the Soviet Union, personal computers to the Soviet Union. And this is actually a memo. This is from I guess it's from the White House Situation Room, 1984. This is a telephone call between the Vice President of the US, George Bush, who would later become president, and the daughter of Andrei Sakharov. And it talks about how Ed Fredkin, Dr. Fredkin, as they called him, it says, a Dr. Fredkin will depart the US today or tomorrow for Moscow at the invitation of the Soviet Academy of Sciences. He's a PhD in computer science, which isn't true, a professor at MIT and owner of a flourishing computer business, but it wasn't really flourishing by that time. He would like to know if the administration would like for him to ask if the Soviets are interested in obtaining anything from the US in exchange for Sakharov. So here was Ed, doing basically, operating as a government operative. And here we go, a document from the White House Situation Room, declassified here, well, declassified many years later, about to the ambassador in Moscow, talking about Ed's visit to Moscow. So I mean, it's quite a remarkable thing that Ed, for all his, if you remember that story of Ed and age 13, putting himself into a strange situation that would generate a strange set of stories. Here he is doing it the same thing many years later with the Soviet Union. So anyway, that's the story there. And Ed, in fact, told me many stories. I wonder if I have more pictures of this, about his interactions with computers in the Soviet Union. I had some of my own interactions with computers in the Soviet Union, but that's again a different story. Sometime after 1982, Ed decided he wants to become a professor. Now, at this point, Ed is kind of Ed decides he wants to become a physics professor, and somehow I wind up writing a recommendation letter for Ed to Boston University, where he wants to become a physics professor. And I say, in this century, people like Ed Fredkin have been very rare. Ed Fredkin is a gentleman scientist. He's made several fortunes in business, at least that's what I thought at the time, before I wrote this obituary. Yet he chooses to spend much of his time thinking about science, et cetera, et cetera, et cetera. And I'm talking about reversible computing. And Ed Fredkin's style is not typical of scientists. He's more used to addressing boards of directors than a lecture audience. He learnt the kind of physics that is in the Feynman lectures by spending time with Dick Feynman rather than reading his books. To some standard scientists, Fredkin at first seems like a nut. To be sure, some of his ideas are pretty nutty, but if you listen and think about it, there is much substance to what Fredkin has to say. I gather that Fredkin has decided to spend some time around ordinary physicists to try and work out how his ideas fit in with current physical thinking. I think you're lucky that Fredkin wants to do this in your department. So then Ed Fredkin kind of associated himself with Boston University for many years, and there's all sorts of stories related to that. Well, I have to say I have many interactions with Ed Fredkin, and I can tell you, maybe it's not worth going through some of these things, but you know, when I was researching new kind of science, I interviewed him in quite a lot of detail about the history of cellular automata, and I can tell you some of the things that I found. Some of the things he told me weren't actually true, but it's always complicated reconstructing this history. This is actually this is where Ed told me that he first did the XOR rule in 1961, which I don't think was correct. Yeah, there's a lot of detail there. And when I've asked him why didn't he look at one-dimensional cellular automata, and he says he didn't think of it. Oh gosh, there's just a lot of detail here. Later on, when my New Kind of Science book came out, I think Ed was a bit miffed, because he kind of thought, well, he'd vaguely been thinking about things vaguely related to this, but actually he really hadn't, because he'd been thinking about kind of trying to construct the universe, which was not at all what I was trying to do. And he was interested in things like, he had the idea of an infoton, that was a unit of information, a particle based on information. Oh, this is just when I sent Ed a copy of my New Kind of Science book. That's the inscription that I wrote to him there. And I think, let's see. Well, probably much later, there's many more interactions. I wrote about some of these in the piece that I wrote about Ed. Yeah, this is now much later. This must be, when was this? This was probably early 2000s. This is a picture of, there's Ed, there's me, that's Gerhard at Hooft, and that's Larry Sulak, experimental particle physicist. And Gerhard, I think he now themes himself as Gerard, but was one of the architects of the standard model in particle physics, and more recently wrote a book about the cellular automaton model of quantum mechanics. I'm not sure I'm a total believer there, but Gerhard is also involved in the cellular automaton business. There's a picture at a conference that about New Kind of Science. That's Ed there. I think whoever is making a point here, everybody is kind of bored by this point, unfortunately. But that's Greg Chaitin. That is, who is that? That's Tony Leggett. That's Tom Toffoli, and that's me there. In any case, so late in life, Ed ended up, he kept on telling me he's discovered the electron. He's found these things that produce circular motion and so on. And he has the cellular automaton that produces a circle. So one of the questions is it true? So this is the cellular automaton running and producing an apparent circle. And it's kind of like, it seems kind of magical that the cellular automaton, it's a 3D cellular automaton, traces out a circle here. So perhaps one thing that it becomes a little less magical when you sort of fill in what it traced out. It's actually traced out a cube. It's traced out a cube with some pieces chopped out of it. That's just the evolution of a 3D cellular automaton. And actually, it isn't quite a circle. And in fact, one can work out that there's a tiny deviation from a circle. As you go around the circle, it has little deviation of about 1% there away from being a circle. And actually, amazingly enough, we managed to figure out that you can actually analytically compute what that deviation is in terms of square roots and logs and things like this from the cellular automaton. So that's let's see, I can show you well, there are more interactions with Ed about different ideas, but I have to say this is what I finally wrote to Ed, and when I sent him a copy of my book about the fundamental theory of physics. It's not cellular automata, but it is computational. Thanks for pushing to apply computation to physics all these years. June 2020. So I have to say, Ed would make up stories. That one of the things that made it difficult for me to assess the validity of stories that Ed would tell is Ed would tell stories about me to me, but they were stories where obviously I was part of the story, and mostly the stories he told about me weren't true. So when I came to research all the other stories about Ed, and all these other stories that Ed had told me, I was very suspicious about them. Most of the ones that weren't about me turned out to at least have a large element of truth to them. This is the very last time I saw Ed. It's kind of a sad picture. That's Ed's second wife, Joyce. Ed was in pretty poor shape at that point, and he died soon after this. 6 weeks later, I think. Ed had told me so many stories. Like he told me that he was descended from a Mongolian, a king of Mongolia. Well, I was visiting his house actually just after he died, and I'm looking at the shelf, and there I find a book by Manny Fredkin, Ed Fredkin's father, that was called Sarah, Queen of Mongolia. And it is a book. I haven't managed to get myself a copy of this book. I've tried to find it, but I haven't been able to find it. I really should ask Joyce if I can borrow it and scan it. But it's a semi-fictionalized account which purports to say that the book blurb actually says here that Ed's father was the great-great-great-grandson of Sarah, Queen of Mongolia. So it's just one of the another just completely bizarre thing about Ed. And it's also interesting that Ed's father, who Ed always sort of presented as being a very uneducated character, had actually got, studied engineering and so on, which Ed never told me. He always said that didn't mention that. And that his father was also writing kind of very kind of Ed-like stories. Now, just to finish this off, I will say, let's just mention Ed's almost circular cellular automaton. There it is at two different sizes. But what is the story of this cellular automaton? Well, it turns out that, let's see, what's actually happening is that the thing is sweeping back and forth through the cube, and it's actually always polygonal, and that's its series of different shapes as it sweeps back and forth through the cube. And the reason that it ends up being circular is, okay, there's the story. That's this little thing that is forming a polygonal shape, but it turns out that if you measure it at these discrete times, that the center point approximates a circle, although it's not exactly a circle. And you can actually analytically solve for that trajectory, and it's a piecewise linear function, and you can compute the deviation from a circle. So in the end, it's not really, it's quite an interesting cellular automaton. It's quite cool that it makes this kind of thing that sort of varies through the polygons and so on. But and it is a reversible cellular automaton, but I don't think it's the electron. All right, I've yacked on at much greater length than I expected. I'm sorry, I didn't really know how much there would be to say about Ed Fredkin, but let me stop yakking there, and if there are any questions, I'd be happy to try and address them. That's a very nice for Vicky. I like your cellular automaton image there. Thank you, sir.
We'd like to take questions from the audience.
I'm not used to giving these more historical descriptions of particularly people that I've known like this, but I'm happy to. There's a lot more to say about the story of Ed's life. I kind of tried to give you some of the highlights. I'm also happy to talk about reversible cellular automata or biological evolution, and sort of things you can discover about elementary cellular automata, even 40-something years after I first introduced them. Ah, Gennaro. Okay, you're very welcome to get off mute and just
Yeah, so I like your lecture very much. Right now I don't have any questions to ask, but I wanted to say that I enjoyed the lecture very much.
Thank you. Okay, 2 questions from Gennaro. Do you know what is the minimal possible reversible universal system? And why Fredkin had a predilection for 3D reversible cellular automata? Okay, minimum reversible universal system, I do not know. It's a very good question. We should know. I do not know. I think that, Ed was very keen on these second-order rules, and I'm quite certain that there's a reversible elementary cellular automaton that is universal, but I don't know which one it is, and I haven't really investigated this. There are definitely class 4 rules, and these mechanoidal rules that I mentioned are examples of that. Class 4 rules where you can see definite structures and where you can imagine sort of building up universality, but I don't know. It's a good question. You should figure it out. Somebody should figure it out. Why did Ed like 3D CA? Because he thought that they were models of space. He really wanted to model physical space, which he thought was 3-dimensional, and he wanted to do it with this rigid grid of cells. Now, in fact, what Ed didn't know, and actually I didn't know this until recently, is that in the early part of the 20th century, many people thought that space was a grid of cells like that. In fact, the history was, in antiquity, people were arguing all the time, is the world discrete or continuous? And, for a long time, nobody knew. Is it fluids? Is it atoms? What is it? By the end of the 19th century, by the beginning of the 20th century, molecules had been established. Brownian motion was the kind of final thing that showed molecules really exist. There really are discrete elements of matter. Photons, light could be thought of as discrete. At that time, beginning of the 20th century, people believed that space would be discrete as well. But nobody managed to figure out how to make that work. And it really wasn't until our efforts in, 2020, that we have a model of space based on hypergraph rewriting and so on, that is a successful model of discrete space. People hadn't thought of using things like graphs in the early part of the 20th century. People like Bohr, Heisenberg, Einstein, all these people, it turns out, I didn't know this until very recently, all these people believed that space was discrete. And they all said, but we can't see how to make it work. Einstein has a quote from 1916 where he says, in the end, it will turn out that space is discrete, but we do not have the methods to analyze that at this time. Heisenberg was trying to show that space was discrete and got so frustrated that eventually he said, let's just understand how particles come into an interaction and go out, and not even worry about what happens in the middle. And that's what caused him to invent the S matrix, which is a major piece of quantum mechanics. But Ed thought that he could actually construct, program, model the universe by an explicit 3-dimensional cellular automaton, which I don't think was a very good idea.
Yeah, it was an amazing lecture, and I just realized that I was a graduate student at MIT LCS during 1980 to 84, and I remembered many of the other names you mentioned, but somehow I can't recollect meeting Ed Fredkin. In which floor of LCS was his office?
Well,
Was
by
he?
1980, okay, good question. By 1984, Ed had sort of, was mostly spending time with his companies and not spending time at MIT. Now,
I joined in
Fano,
80. I joined in 1980, and I was in the
Okay.
theory of computation group on the, I guess it was on the 8th floor. Almeyer's group. Ron
in
Rivest.
Albert Meyer's group. Okay, well, Albert Meyer.
Albert Meyer. Ron Rivest was my advisor.
Aha.
And AI lab was just on the other side of the 8th floor. So I was wondering where Ed Fredkin was on which floor.
Yeah, I don't think I ever, I spent time at 545 Technology Square a bit earlier than that time. But I don't remember ever meeting Ed at in that building. Now, if you ask about Fano,
I think he was on the 4th floor.
Okay, so I believe that Ed knew Fano, and I believe I met Fano when I believe Fano came to visit Ed's island at the same time that I was there. So he knew Fano. I don't know. I mean, Ed actually, now that I remember it, Ed told me something about Ron Rivest. And in fact, Ed, I'm trying to remember this. Whether did I write about this? I'm trying to remember if I wrote about this. Let's see. Yes, here we go. I asked Ed in this is when was this that I asked him this? In 2000. I asked Ed, were you aware of work on cryptographic applications of cellular automaton-like systems? And Ed responded, I thought I invented that idea. As soon as I found ways to make reversible universal cellular automata, it occurred to me that they could be used for cryptography. As an aside, he says, when Whit Diffie came up with the idea of public key cryptography, which needed a trapdoor function, I thought of using the product of two large primes. I had just written the first program in Lisp to implement Michael Rabin's first version of a probabilistic prime test. As soon as I implemented it, I started a search at 10 to the 100 and discovered that such and such a number was prime, and Rich Chappell, who was working for Ed's company, knowing blah, 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 blah. Knowing a larger prime pair than anyone else on Earth, I told Rich Chappell this and he was blown away. Okay, let's see, where is it? Okay. Anyway, he says in what he sent me, he says, I'm rambling, probably about stuff of no interest to you. Anyway, I stopped Ron Rivest in the hallway at Tech Square and asked if he had heard of Diffie's stuff. I don't remember exactly what he said, but I know that when I told him that Rabin's new method to find large primes meant that the product of two primes was a good trapdoor function, he was surprised and thought it was a good idea. I never thought any more about it and hadn't come up with the idea of using the phi function. Years later, long after RSA was a big thing, Ron reminded me of the event. Don Knuth told me that he also thought of using the product of two primes before RSA, but he couldn't have known about Rabin's method when I did, as Rabin told it to me right when he thought it up. So anyway, so apparently he had some interaction with Ron Rivest, but I don't think it's a small world. But the thing about Ed's stories is that Ed's stories were always it took effort to kind of take these stories and kind of turn them into but I don't remember Ed ever interacting with I mean, I knew people like Shafi Goldwasser and so on, who was sort of in that orbit, and I don't remember Ed ever interacting with that crowd. I mean, I think by that time, well, in 1980, Ed was surely still quite involved with MIT, and did that conference on physics of computation in 1981. But I think he was mostly, at that time he was also very involved with the Three Rivers Computer Corporation, which was and I think he was really just running his companies, and I think he wasn't much around MIT at that time. But that's an interesting kind of connection.
Thank you.
Sure. I don't know one name that you mentioned there, Steve Ward. I don't know that name.
He was my faculty advisor. I think he was what was it called? Director of the LCS at that point of time when I joined.
Interesting. Well, I mean, there were another person who was involved with Cellular Automata there was Frank Henney, who is still alive, and I exchanged mail with him recently, although I have to admit that I didn't. So he wrote a book about, what did he call it? Oh my gosh. He wrote a book around 1960 about cellular automata, although, I'm sorry, Frederick Henney. Yeah, that's right. He called them iterative arrays.
Yes.
And but I don't know why he studied them. And I had asked him. I remember now. Just when I was writing this obituary of Ed, I had found that Frederick Henney was still alive, and I sent him email, and I basically said, "Why did you study these things?" And I think he told me that. Oh gosh, I have to look it up. I'm going to tell you because this is my one moment for knowing this history. So I'm just going to look at my archive right now and see what I can see here. Here we go. To Henney. Maybe I never got a response to these. I asked him some questions and then, oh no, here we go. From Henney. Oh, that's very odd. I don't believe I got an answer to this. Let's see, am I reading this correctly? Yes. Huh. Well, I should follow up on that. Okay, so I don't know the answer to why. I think I did work out something about why Frederick Henney had gotten into iterative arrays, and I'm now forgetting it. So I'm sorry, I don't know that. Let's see. Suvik asks, you mentioned, can machine learning predict what will happen in a complex cellular automaton? Well, it just so happens that I've studied that recently. So why don't I show you something about that? There we go. Share that screen. Let me see what I can pull up. Okay. So let's say you're trying to predict something with a neural network. Let's say you're trying to predict a sine wave. You might have a neural net. You train the neural net. That's a representation of a neural net with one number as input, one number as output. This is training of the neural net. Actually, it does a pretty crummy job at predicting a sine wave. It really depends on, if you have different neural nets, they'll do differently.
But we are seeing that many Fredkin.
Okay, wrong screen again. Boy, this is a confusing interface. Wait a minute, what are you seeing here? Hold on, what are you seeing? Just a second, I see what you're seeing, but stop. Okay, present something else. Entire screen. Okay, there we go. Okay, all right, maybe you see that. Let me try this again. Okay, so we're trying to predict a sine wave. We have a neural net. We train the neural net based on the early part of the sine wave to predict the later part of the sine wave. This is a neural net where it has one input, one output, and and these colors represent the weights in the neural net. Based on that neural net, you've trained it on the early part of the sine wave. As soon as you get to the part where you haven't explicitly trained, its extrapolation is really crummy. Actually, extrapolation depends. You choose different neural nets, they'll have different extrapolations, but they're always pretty crummy. So now let's do it on cellular automata. Okay, so this is now a transformer net. This is all just Wolfram language code. You can do it yourself too. This is what happens with a transformer. So transformers are the kind of the well, until very recently, the most popular kind of architecture for neural net systems. I think diffusion architectures are becoming a little bit more popular the last couple of months. But in any case, this is trying to predict a cellular automaton. A transformer is kind of a look back. It's a little bit like a one-dimensional cellular automaton, except it's got a bunch of real numbers in it. And it's kind of looking back, and it is able to predict correctly a periodic piece in a cellular automaton. Now, it turns out this is a cellular automaton. This is a neural net which has more and more training examples, tens of millions of training examples of the behavior of this particular cellular automaton. And you can see that as you give it more and more training, it becomes better and better at predicting these periodic pieces. But when you have more complex patterns, it just doesn't work. It just doesn't succeed. That's sort of the ground truth of those patterns, and it really doesn't work very well. And I think that's a general feature of computationally irreducible systems, that when there's computational irreducibility, you really can't expect a neural net to successfully kind of jump ahead of the computation and predict what's going to happen. I mean, you can try and do that. Let's say you're solving the three-body problem with differential equations. You can try and predict that with a neural network, and you see kind of the lines here are the neural net prediction. And in places where the behavior is quite simple, it does okay. But in places where the behavior is complicated, it has sort of random variation relative to the complicated behavior. So that seems to be sort of the typical thing that happens. And you can look at lots of different kinds of cases and try and understand sort of what. So the answer is neural nets cannot predict. I don't think. Unless you're running a cellular automaton inside the neural nets, which you can set up neural nets to do, unless you're explicitly doing that and taking the computation time to run the cellular automaton, you can't expect the neural net to kind of jump ahead of the cellular automaton and figure out what it's going to do. You can also imagine doing things like finding regularities in cellular automata using neural nets. This is about autoencoders for cellular automata, and kind of summarizing that pattern with just two numbers, and then you try and reconstruct from that, and you get sort of an approximation. You can kind of see a little bit about how that works. But yeah, so I think the answer is you can't expect neural nets to kind of outcompute the irreducible computation of a cellular automaton. And I think you can do things like use neural nets to classify cellular automata. I've tried to see can I do the equivalent of my visual kind of classification of rules, and I think yes, one can do some of those kinds of things. Okay, I've shown reversibility as circularity. What is about backward transitions and injectivity? You know, Ed's example of the circular of the thing that goes in a circle is really a very kind of a very strange example of reversibility. What I was showing earlier when I was talking about the second law of thermodynamics is much more typical of what one's dealing with reversibility, where one's just got a state of the cellular automaton that evolves to a unique state and can evolve backwards. And I think I showed earlier some state transition graphs of cellular automata where you can see that there are no transient trees. There's just a collection of circular pieces that represent the kind of state structure of the cellular automaton.
But what if the space is infinite? Then there is no question of coming back to initial condition. So how
Sorry,
can you
say that again. I'm just having a hard time hearing the audio. So could you just say that again?
See, what if the space is infinite? So the question of coming back to the initial condition, it happens if the system is, the space is finite. But as the example you have shown related to your second law, and then the initial condition is coming back, and that you are referring to the reversibility. But in that case, we cannot go back because the system is not injective. If you're not injective, then you can't go back. The thing is that if the system is infinite, then it may so happen that the initial condition is not coming back. So how can we relate this kind, the coming back condition and the infinite system. As you mentioning, the reversibility means coming back to the initial condition.
Okay, so I mean, the finite case is easier to look at because you can just see the complete state transition diagram. This question of injectivity for infinite systems is something, gosh, I studied this in quite a lot of detail in 1984. I wrote a paper called Universality and Complexity in Cellular Automata, and that talks about kind of the calculation of entropy. So the way you do it is, it's been a few decades, so it takes me just a moment to remember how this works. It has what you do. So, for example, you can represent the possible states of the system by a finite state machine. So even though there are an infinite number of possible states, you can say the states are those things which are accepted by a certain finite state machine. And so by looking at that finite state machine, you can compute the entropy, basically that you can compute the number of states consistent with the number of possible states of any size n arbitrarily large in the system. And when you compute that, the injectivity condition is that that number of states remains constant. So I think if you good place to look always. Let me see if I can share again here. See if I mess this up again. Let's see if I can do this without messing it up. Let's see. Let me pull up something here. How do I do this? All right. Trusty reference source for these kinds of things. Let's just look up injectivity in the index and maybe it'll have a nice definition of what's going on. Injectivity in Cellular Automata, page 959, always a good start. Surjectivity and injectivity of cellular automaton maps, always a good start. Okay. So we could think of a cellular automaton mapping as an endomorphism, et cetera, et cetera, et cetera. Oh yeah, that's right. I remember this. Right. Okay. So there are a certain number that are surjective, and there's a certain number that are injective. And I think I give some examples in, oh gosh. I think I give some examples of this in the book of, yeah, I think these are examples of reversible rules. Yeah, those are the simplest, those are the elementary rules that are, that are reversible, but you can find injective, infinite injective rules here. And there's an algorithm in one dimension for finding those injective rules, which I described in the NKS book, and I described it earlier in that paper that I was talking about. But these are examples of injective, infinite injective cellular automaton rules. So if you do that in one dimension, there's an algorithm to find these rules. In two dimensions, it's related to the tiling problem, and it's in general an undecidable problem whether there exists, whether a particular rule is injective or not. In one dimension, there's an upper bound on the number of inverse images that you have to check. In two dimensions, there is no such upper bound. Fun fact is that in the late 1950s, people were interested in designing cryptographic systems, and they wanted to design, well, they mostly were designing things that were based on shift registers, nonlinear shift registers. And in the US, in particular, a bunch of pretty well-known mathematicians were recruited by the National Security Agency to kind of study these things. And they, in fact, studied some cellular automata, and they actually enumerated some reversible injective cellular automata. This is in the, I think, 1962-ish time frame. And they had some tables of the injective cellular automata from that time. And in fact, when the data encryption standard, DES, was invented in, I think, the late 1960s, early 1970s, they used those injective cellular automata to determine the S boxes of DES. And for many years, people were like, we don't understand where the S boxes came from. And there were many conspiracy theories about the S boxes and whether they were put in there in a particular way so that people could break those codes and all those kinds of things. Actually, the S boxes came from that study of injective cellular automata. And to tell you a piece of, some piece of the story I'm not going to tell, but let's just say in the 1980s, I was visiting Yale one day, and there was a person there named Gustav Hedlund, who was the person who had been part of that effort to do the computations of the injective cellular automata back in that time in the late 1950s. And I kind of arranged to see him, and he said, well, I can come and see you, but I haven't been into my office for 10 years. So I show up, and the very old Gustav Hedlund shows up. His office is covered in dust, and we have a very strange conversation. At least it starts off very strange, and he doesn't really understand why I'm there, but eventually he kind of explains what he was doing in kind of tells me the whole story of what had happened with the developments of these S boxes and so on. And then the end of that, actually, he says, well, I'll probably never be back in this office again. So if there are any books you would like to have from my shelves, please take them. So I took a big pile of books. And so now somewhere on those shelves behind me, actually, there are some books from Gustav Hedlund that I picked up that day when I went to see him and learned about injective cellular automata. So let's see, from Kamalika, questions to ask. Why do I think that the macro world exhibits irreversibility, whereas the micro world is reversible? Well, I wrote this whole book about that. So I was telling you some pieces of it, but there's a whole book. You can find all the pieces of that online. Let me not go into that now, because that's going to be a long discussion. I have to make sure that I mean, essentially what happens is that it is still reversible, but we don't notice that it's reversible, because to notice it's reversible, we would have to kind of break computational irreducibility, which we can't do. Let's see. Do I think the block cellular automata where each component is reversible is a special case of 1D CAs? Well, yes, you can represent, you can convert between block cellular automata and ordinary cellular automata. It's kind of just a two-step thing. A block cellular automaton has even and odd steps. If you compose those two steps, you can certainly get a 4-color cellular automaton, and quite possibly in many cases there's a 2-color one that corresponds to that. Okay, you're asking about commutation of rules help do classification of patterns. I don't know. I mean, one of the things that we learn from that minimal model of biological evolution is that I think it's also very related to how machine learning works, something I'm about to study, and hopefully I'll have some results on that in a few weeks. The study of mutations of cellular automaton rules, I'm kind of embarrassed that I didn't study these things 40 years ago, because I almost did, but I didn't have the intuition that if you sort of do enough mutations, you'll make progress. That's an intuition that I have now from doing machine learning, but we just didn't know that. Until 2011, it wasn't clear that, if you did 1 million steps of machine learning, you would think you'll get as far as you can get. And there won't be, you're stuck at that point. But in fact, the big discovery of 2011 was that if you do billions and billions of machine learning steps, you'll get somewhere that you wouldn't have seen with only millions of steps. And so that was kind of the intuitional change that led me to actually try this biological evolution thing just a couple of months ago and find out that, my gosh, it actually works to just do these mutations. And it's an unbelievably simpler model of evolution than people have had before. Previous models of biological evolution have a lot of detail in them that really, I think, obscures what's really going on. Let's see. Supriti says, with the circular pattern, Fredkin thought he had discovered the electron, mentioned it was a cellular automaton. However, you mentioned it was not a cellular automaton, but a computation. Oh, no. The thing that I was showing that is that circular pattern is a cellular automaton. It's a three-dimensional cellular automaton. It is, it's just, it doesn't have much to do with physics. It's a cool phenomenon in a three-dimensional cellular automaton. Let's see. Cellular automata have been proven to be effective random number generators. Yep, that's what I worked on in Rule 30 and so on back in the 1980s. But why have cellular automata not been much used in cryptography in general, although several efforts have been made? And why have reversible cellular automata not been relevant? Okay, so, gosh. So let me tell you a couple of stories about that. First of all, Rule 30 has been fairly widely used as a random number generator. In cryptography, it's not been easy to see how to use cellular automata. I'll show you something about that. Let's see if I can find it here. This up again. Okay, see, I'm gradually learning, like a machine learning system, not to press the wrong button to get the screen, to get the correct screen shared. Okay, there we go. All right, let me see if I can find something here. Okay, so this actually relates to my second law story. That was, I showed you that book. And by the way, just for your amusement, that's the computer that I first programmed I ended up programming cellular automata in 1973 on that computer with paper tape. Maybe that's a cellular automaton program. I haven't been able to decode it. I still have that paper tape. That was subsequently, that was the computer that I did a lot of cellular automaton work on. You can see the old-fashioned telephones and all that kind of thing. That's 1982, I think. But in any case, at some point, that's me with some of those. That's me with a cellular automaton a little bit later than that, I think. Me with more hair and much bigger displays for my cellular automata. That was actually just for fun. That was the original invention of the term computational irreducibility for an article that I wrote in Scientific American in 1984. But the thing that I want to highlight, people were thinking about cryptography. This was a strange company started by a rather sketchy physicist friend of mine. This is 1982, talking about stream encryption and so on. Now, a little bit after that, a person called John Milner, very well-known mathematician actually, was sort of working with me on cellular automata when I was at the Institute in Princeton, and he got very, very into cellular automata, and he would leave me these notes every day about features of cellular automata. And we started working on, this is a paper you've never seen because it never got finished. It was a paper that Jack and I were writing about cryptography with cellular automata. And so we tried to make this work. And these were some pictures. I think those are pictures I drew of different sort of setups for cellular automata. And it's probably a bunch of other things here. Oh, look, bijectivity measures. There we go. That this is talk about injectivity and bijectivity. There's the very thing, May 7th, 1984. Gosh, that's almost exactly 40 years ago now. So we were looking at these things, and I think that's a Rule 30 from July of 1984. We're about to come up to the grand anniversary of when I finally figured out that Rule 30 was interesting, which was June 1st of 1984. But in any case, what is this? Let's see. That's probably not relevant. In any case, we failed. We couldn't figure out how to make cellular automata work as crypto systems. And I think the real problem is that with one-dimensional cellular automata, it's not obvious how to do something like the sort of trapdoor function of, because it's too easy to invert a cellular automaton. It's too easy to find the inverse rule, at least in one dimension, because there's a bound on the, if you have a rule with a certain radius, there's a bound on the radius of the inverse rule in one dimension. In two dimensions, there isn't such a bound. So I think it's more possible that one might find a way to get sort of the inversion problem to be difficult in two dimensions. But I never figured out how to do that. It's a remaining sort of story. Oh, there's a question here from Sukanta about how do you relate our physics project with Ed's digital physics? Well, the basic point is Ed was starting from a fixed structure of space and time as the grid of a cellular automaton. That doesn't work. What's ended up with our physics project is that it's really a story of the kind of the dynamics of the structure of space represented as a hypergraph. And it's a much more general structure for space. And that's why it's able to work. And it's really, you know, when Ed was talking about cellular automata for physics back in the 80s, I was always very frustrated because it's like, look, Ed, it can't possibly work. But cellular automata are really interesting. And Ed was never interested in kind of just studying cellular automata for their own sake. He just wanted to use them as a programming mechanism to program the universe. And it's just like, that's not going to work. And it actually probably delayed my effort to try and find a computational model of physics by a decade, because I was kind of like, I was kept on, no, it's not going to work, it's not going to work, etc. It was in the beginning of the 1990s that I started thinking about networks as sort of a raw material for making up space-time. And that's the thing that has really led to sort of these breakthroughs.
But in both the cases, the physics is computable, right? In your physics project as well as Fredkin's digital physics. So in both the cases, the physics is computable, right?
Well, except that in our project, we can reproduce general relativity and quantum mechanics and things like that. Ed never got anywhere close to anything like that. I mean, Ed was just saying there's a cellular automaton and it's got patterns in it. I mean, that's a, you know, so it isn't really what Ed was doing is, yes, it's computational, absolutely, but it's not physics. So it was just a, you know, it was, let's say, it was kind of you know, one or two lines of a cartoon that one day would be a big painting that makes physics. And he was doing one or two lines of the cartoon. Now, you know, the big mistake that Ed made was believing that you could engineer physics. That was the big mistake, that you could program physics. You could write a program. You could sit down and write a program and have it be physics. That just, you know, he didn't understand this point that there is kind of emergent structure that goes far beyond the rules. He just imagined, given physics, he can reverse engineer that and figure out what the underlying rules are as a cellular automaton. That was the big mistake. And it was, you know, it was, I mean, Ed was a programmer and an inventor, not really a scientist. He never kind of signed up to be a natural scientist. He never did natural science. He never went from a phenomenon to understand how it worked. He was always trying to invent and build things from a concept to an engineered structure. And that is a different activity from, for example, a lot of what I've been involved in of just do the experiments, see what happens. Ed didn't do that. Ed was always trying to control what would happen, to program what would happen. And so it's a kind of a different approach. And it's I think Ed never really understood that distinction. I think he always sort of felt that the stuff I was doing was kind of like what he was doing because it was about cellular automata. And it really wasn't. I mean, and I don't think Ed, I mean, it's kind of ironic because, you know, in his sort of push towards programming, he used Mathematica and Wolfram Language for 35 years. So he was, you know, he knew well many of the things that I've constructed as pieces of engineering, but he didn't really, I don't think he ever, you know, I would say perhaps the fairest thing to say is that I never understood the point of what he was doing, and he never understood the point of what I was doing, because I just didn't think you could program the universe the way that he thought you could program the universe. And he didn't think that studying kind of the natural history of cellular automata would lead to anything. And so I think it's just very different approaches. And I think Kamalika asks about digital philosophy. I'm not completely sure. I mean, Ed in his later years, it got kind of complicated because by some point, Ed knew quite a bit about what I had done. And so it was sort of a mixing of things that I've talked about, things Ed had talked about earlier. And I think somehow they sort of mixed into digital philosophy. And I don't really know the full story of what Ed had wrote about in later, sort of talking about digital philosophy. I think his main point was that kind of there's sort of that you can think about the world in computational terms, and you can kind of track down how much information there is in this or that thing. I'm not sure that, I don't know. Well, Kamalika asks, what are my comments on the future of reversible computing and quantum computing? Reversible computing. I'm pretty exposed to the front lines of what's happening in microprocessor technology and so on. And right now, nobody cares about reversible computing there. Right now, the issues of, can you reach 3 nanometer feature size, all these kinds of things are very, there is certainly an issue of getting the heat out and so on, but it's not really on the roadmap to think about reversible computing. And in fact, I was literally just talking to some people who are working on kind of the roadmap to going out to 2036 for microprocessor technology, and this isn't part of the roadmap. So that's not yet a thing that people are thinking about. Should it be? I don't know. Good question. I mean, I don't, the question of whether, I think, let me just think about this. I think the problem is this, that reversible computing run at 0 speed dissipates no energy. But if you want to push the reversible computer in a particular direction, you have to expend energy. And that energy is going to end up just in the details of electronic circuits, having capacitive losses and things like this. And you're going to have to pump energy into the system to get it to move forwards at a reasonable speed. So I'm sort of skeptical that that's going to be, I don't know. I mean, it's a reasonable question. And it's a reasonable thing to look at the microprocessor roadmaps and see if there's a way to inject this. In terms of quantum computing, well, the standard formalism of quantum mechanics, the unitary evolution of quantum mechanics is reversible. So it's a whole story of reversible gates. We've done lots with that, both in Wolfram Language and in a physics project and so on. Here's the real thing about quantum computing. So again, I seem to be living back in the 1980s a lot, but I guess that's the origin of a bunch of things that I've done. Maybe in a few years I'll be saying, back in the 2020s, we were doing this or that thing. But at the beginning of the 1980s, I worked a bunch on quantum computers, actually with Dick Feynman mostly, and I didn't think they were going to work. And in fact, I found very recently, I found a referee report that I wrote in 1982, I think, for a paper by a guy called Paul Benioff, which was about quantum Turing machines. And actually, what I said, which was a footnote to history, but it's a shame for history. I said, this paper is about a very interesting topic, but the paper is incomprehensible. If the author really wants to publish this paper, they should go ahead. But let me give a better description of what the author should have said. And in fact, it's a shame that the author, who I corresponded with a few years ago, in his mid-90s, it's a shame he never took my advice. He published the paper in its incomprehensible form, so nobody's ever heard of that paper. had he actually fixed it, it would have been a very clean paper about the beginnings of quantum Turing machines, but he didn't. So that's just one of those footnotes to history. And I suppose, anyway, I didn't think quantum computers were going to work because I thought that the measurement process was going to take as much effort as the actual quantum part of the computation would speed up. I still think that. So here's the basic description. In our model of physics, we understand much more clearly how these many threads of history operate in a quantum computer. If we had quantum brains, we would be able to operate. If we had sort of a quantum consciousness, we could be aware of all these different threads of history. But what we don't, we have we believe that history operates in a single thread, that there is a definite answer to our computation. So at the end of all that quantum parallelism, we have to knit all those threads of history together into a single sort of thread of experience. And the effort to do that is something that is not accounted for in quantum mechanics. In quantum mechanics, in the standard formalism, it's just you project and you do a measurement. And that's just a sort of atomic act. It's not something where you understand the mechanism for that measurement. So the real question is, what is the mechanism for measurement? In other words, if you actually do the measurement, how much effort do you have to spend knitting together those threads of history? And do you actually gain anything in the end? Or is the effort to knit the threads of history together as much work as it would have been to do the computation sequentially? Okay, so what's actually observed on the ground for quantum computers? Every quantum computer observes noise. Every quantum computer has decoherence times. The question is, people say, well, if we do the engineering better, we're going to get rid of the noise. We're going to increase the decoherence times. Is that really true, is the question. And so I have an analogy I've been giving recently, which is sort of a physics analogy, but it's, imagine you're building telescopes and you want to build a telescope and it's going to see sand dunes on the planet Mars. And that's really hard, right? And you might say, well, our current telescope doesn't quite make it, but we're going to improve it. We're going to polish the mirror more carefully. We're going to make the whole thing. We're going to do error correction. We're going to do this and that and the other. But in the end, you'll never see the sand dunes on Mars with an optical telescope from Earth because of diffraction, because there's an actual physical phenomenon that limits the resolution of telescopes. So I'm pretty sure that there's a physical phenomenon that limits the effectiveness of quantum computers. And actually, I think the most interesting thing that will have been discovered in the current age of quantum computing is that limitation. And so I'm actually about to try and do a project. If anybody wants to be involved in this, I'm interested in finding people to help, of going and exploring every single actual practical quantum computer and finding out what are its noise limitations and so on. Because I think if you plot them in just the right way, you're going to see that there's some actual fundamental thing. I think it's like discovering H-bar or something, discovering the quantum, and actually I think in our physics project, it's related to this thing called the maximum entanglement speed, which is kind of the analog of the speed of light in the space of quantum branches. And so my guess is, my hope is, if we're really, really lucky, we'll actually be able to find the value of the maximum entanglement speed from these quantum computer experiments. If we find the value of the maximum entanglement speed, we will find the elementary time and the elementary length. We'll actually know what the discreteness scale of space-time is. So that would be pretty exciting. I'm not sure if it will work that way, or whether it's still the case that quantum computers are far above the sort of ultimate limit imposed by maximum entanglement speed. But that's my feeling about that. And I think that the formalism of quantum mechanics with its reversibility is all well and good. But if you actually want to make a quantum computer, you have to do the measurement, which is not reversible. The measurement is irreversible. And if it wasn't irreversible, we wouldn't have a definite conclusion about what happens. So that's kind of the way I think that works. All right, it's getting close to my bedtime here. So we have to, we should wrap up soon.
Yes. Thank you so much, Stefan. It was a very insightful discussion and a very nice talk. So with that, we will conclude today's session. And just to announce that our next session is on 18th May, and it will be started with Tom Toffoli, followed by Smita Sarkar, and the time is from 2:30 p.m. IST. Okay, so thank you everyone. Thank you so
Nice
much.
to
Thank you
chat
so
with
much,
you all. And
Stefan.
I just want to,
Bye.
I'm going to give one promotion here. Remember our summer
Sure.
school for those of you who are interested in studying these things more. Always a good thing to think about. But anyway, nice to chat with you guys, and look forward to hearing from you all again.
Thank
So,
you.
bye for now.
Thank you and good night.
Thank you.
Good night.
Thanks. Bye.
Good night.